Nike sneakers are some of the most recognizable products on the planet, worn by professional athletes, casual runners, and everyday consumers across nearly every country. Yet behind every finished shoe is a massive, highly coordinated industrial manufacturing system that blends material science, precision engineering, automation, and skilled human labor. What looks like a lightweight, flexible sneaker is actually the result of hundreds of components coming together through tightly controlled processes designed to deliver comfort, durability, performance, and visual consistency at enormous scale. And today on The How Factory, we're going inside modern footwear factories to see exactly how Nike sneakers are mass-produced, from raw materials to the finished pair boxed and shipped worldwide. The process begins with materials sourcing, long before a shoe ever takes shape. Nike sneakers are built from a wide mix of components, including engineered mesh fabrics, synthetic leathers, foam compounds, rubber outsoles, thermoplastic reinforcements, adhesives, and molded plastics. These materials arrive at factories from specialized suppliers around the world. Rolls of textile fabric come tightly wound and wrapped to prevent contamination. Rubber compounds arrive in slabs or pellets. Foam materials used for midsoles, such as EVA or proprietary cushioning blends, are delivered in raw form ready for molding. Every incoming material undergoes inspection for thickness, density, elasticity, color accuracy, and defect tolerance. Even slight inconsistencies can affect fit, comfort, or performance, so quality control begins at the loading dock. One of the first major stages is upper production, the creation of the shoe's fabric body. Modern Nike sneakers often use engineered mesh or knit uppers designed for breathability and flexibility. In textile departments, computerized knitting machines or automated weaving looms produce fabric panels with varying density zones. Some areas are tightly woven for support, while others remain open for airflow. These machines follow digital patterns down to the stitch level, allowing designers to control how the shoe flexes during movement. For cut-and-sew uppers, large fabric sheets move into CNC cutting machines, where oscillating blades or laser cutters slice panels with extreme precision. Each panel corresponds to a specific part of the shoe: toe box, midfoot, heel counter, tongue, or collar lining. Once cut, upper components move to assembly lines. Here, heat presses bond reinforcement layers to high-stress areas like the eyelets or heel. Synthetic leather overlays may be added for structure. Logos, swooshes, and branding elements are applied using heat transfer films, or stitched directly into the upper. In some models, welded seams replace traditional stitching to reduce weight and eliminate pressure points. Industrial heat presses activate adhesives that permanently fuse layers together. At this stage, the upper still lies flat, resembling a complex fabric puzzle rather than a shoe. While uppers are being built, sole components are manufactured in parallel. The outsole, the bottom layer that contacts the ground, is typically made from durable rubber compounds. Rubber pellets or slabs are fed into molding machines where heat and pressure form them into patterned outsoles. The tread design, traction zones, and flex grooves are molded directly into the rubber. Each outsole is cooled, trimmed, and inspected for uniform thickness and surface defects. For performance models, different rubber densities may be combined to balance grip and durability. Above the outsole sits the midsole, the cushioning heart of the sneaker. Midsoles are usually made from foam compounds designed to absorb impact and return energy. Raw foam materials are injected or compression molded into midsole shapes using steel molds. These molds define not only the silhouette of the shoe but also internal geometry that affects cushioning response. Some midsoles incorporate air units, gel systems, or layered foam constructions. Air units are manufactured separately by sealing pressurized gas inside tough plastic membranes, then tested for leaks before being embedded into the midsole. Once molded, midsoles are cured, trimmed, and checked for density and rebound performance. Next comes one of the most critical stages: lasting. This is where the flat upper becomes a three-dimensional shoe shape. The upper is pulled over a foot-shaped mold called a last. Machines or skilled workers stretch the material evenly around the last, securing it temporarily underneath. This process defines the shoe's fit, toe shape, and volume. Wrinkles or misalignment at this stage can ruin the final product, so precision is essential. Adhesives are applied to the bottom edges of the upper in preparation for sole attachment. Once lasted, the upper meets the sole. Adhesive bonding is the most common method in modern sneaker production. Both the bottom of the upper and the top of the midsole are coated with specialized industrial adhesives. These adhesives are carefully formulated to remain flexible while maintaining long-term strength. After application, parts pass through heat activation tunnels that prepare the adhesive for bonding. The upper and midsole are then pressed together using hydraulic or pneumatic presses that apply uniform pressure. In some designs, stitching is added around the sole edge for additional reinforcement and style. After sole attachment, the shoe moves to curing racks. Adhesives require controlled time and temperature to reach full strength. Shoes rest on racks for hours or even days depending on the materials used. During this time, inspectors check alignment, sole symmetry, and bonding quality. Any separation, unevenness, or cosmetic flaw can send the shoe back for rework or rejection. Next, the shoe enters finishing and detailing. Excess adhesive is cleaned from seams. Edges are trimmed. Insoles, often made from foam or molded footbeds, are inserted. Laces are added. Tongues are adjusted. Size labels, country of origin markings, and compliance tags are attached. For performance models, additional components like stability plates or heel counters may be installed internally before final closure. At this point, the sneaker looks complete, but it still must pass testing. Quality control teams perform visual inspections, flex tests, and dimensional checks. Random samples undergo mechanical testing, where machines repeatedly bend the shoe to simulate thousands of steps. Outsole abrasion tests measure wear resistance. Cushioning is tested for compression and rebound. Fit consistency is verified using standardized measurement tools. Any batch showing abnormal results is isolated and investigated. Once approved, sneakers move to cleaning and preparation for packaging. Shoes are wiped down to remove dust or residue. Tissue paper is inserted to maintain shape. Each shoe is paired with its mate and placed into a branded box along with spare laces or inserts if required. Boxes are labeled with model number, size, colorway, and barcode information. Automated scanners verify that box contents match the label exactly. Packaging lines then group individual boxes into larger cartons. These cartons are stacked onto pallets by robotic systems optimized for stability and space efficiency. Stretch wrap secures the pallets for transport. Throughout this stage, warehouse management systems track every unit using digital inventory controls. Each pallet can be traced back to a specific factory, production line, and date. Behind the scenes, logistics coordination keeps everything moving. Nike operates a global supply chain, with factories often located near material suppliers and shipping hubs. Finished sneakers are transported by truck, ship, or air freight to regional distribution centers. From there, they move to retail stores, online fulfillment centers, and partners worldwide. Timing is critical, especially for new releases tied to marketing campaigns or athletic seasons. Sustainability also plays an increasing role in modern sneaker manufacturing. Factories work to reduce material waste by optimizing cutting patterns. Scrap foam and rubber are collected and recycled where possible. Water-based adhesives replace solvent-based ones in many models. Energy-efficient machinery and LED lighting reduce power consumption. Some Nike sneakers incorporate recycled plastics or sustainable textiles, requiring additional sorting and material handling steps within the factory. What makes Nike sneaker manufacturing remarkable is the balance between scale and precision. These factories produce tens of thousands of shoes per day, yet each pair must meet exact standards for fit, comfort, and appearance. A shoe must feel identical whether it's bought in New York, Tokyo, or Paris. Achieving that consistency requires not only advanced machinery, but also trained workers, digital process control, and constant monitoring. From engineered fabrics and molded foam to adhesive bonding, lasting, testing, and packaging, the journey of a Nike sneaker is far more complex than most people imagine. It's a system built on material science, biomechanics, automation, and logistics, all working together to turn raw materials into performance footwear worn by millions. And that is exactly how Nike sneakers are mass-produced in modern factories. Cut, molded, assembled, bonded, tested, boxed, and shipped at global scale through a finely tuned industrial process hidden behind one of the world's most iconic products. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines and systems behind everyday products. Cigarettes may look like one of the simplest consumer products in the world, a small paper tube filled with shredded tobacco and sealed inside a cardboard pack. Yet behind every finished cigarette lies a massive, highly automated industrial process involving agriculture, chemistry, precision cutting, high-speed machinery, strict quality control, and global logistics. From harvested tobacco leaves drying in curing barns to ultra-fast cigarette makers producing thousands of units per minute, the modern cigarette industry operates with a level of engineering and scale few people ever witness. And today on The How Factory, we're going inside that system to see how cigarettes are made, tracing the journey from raw tobacco leaf all the way to the finished sealed pack, ready for distribution. What appears simple on the outside is actually the result of decades of industrial optimization and tightly controlled manufacturing. The process begins far from the factory floor in tobacco-growing regions around the world. Tobacco plants are cultivated on large farms under carefully managed conditions. Different varieties, such as Virginia, Burley, and Oriental, are grown for different flavor, burn, and aroma characteristics. Farmers monitor soil nutrients, rainfall, and plant health throughout the growing season. When the leaves reach maturity, they are harvested either by hand or by machine. The leaves are then cured, a crucial step that transforms fresh green leaves into usable tobacco. Curing methods vary by tobacco type. Flue curing uses heated barns to dry leaves quickly while preserving sugars. Air curing allows leaves to dry slowly in ventilated barns. Sun curing relies on natural sunlight, while fire curing exposes leaves to controlled smoke. During curing, moisture content drops dramatically and chemical changes occur that affect flavor, color, and combustion properties. Once cured, the tobacco leaves are bundled and transported to processing facilities. At these plants, the leaves are unloaded, inspected, and graded by size, color, and quality. Foreign material like stems, dust, or damaged leaves is removed. The tobacco is then conditioned, a process that reintroduces controlled moisture to make the leaves flexible enough for mechanical handling. Conditioning chambers carefully adjust humidity and temperature so the brittle dried leaves don't shatter during processing. After conditioning, the leaves move to primary processing. Large machines strip the central stem, known as the midrib, from each leaf. The stem contains less desirable material and burns differently than the leaf itself, so it's separated for other uses or disposal. The remaining leaf lamina is cut into smaller pieces and blended. Blending is one of the most important stages in cigarette manufacturing. Different tobacco types from different regions are mixed together according to precise formulas. These blends are designed to produce consistent taste, aroma, burn rate, and smoke characteristics. Industrial blenders resemble giant rotating drums or conveyor-based mixing systems that tumble tons of tobacco until the mixture is uniform. Even small variations in blend composition can alter the final product, so blending is tightly controlled and continuously monitored. Once blended, the tobacco enters the casing and flavoring stage. Contrary to popular belief, this step is not simply about taste. It also affects moisture retention, burn behavior, and smoke consistency. The tobacco is sprayed or misted with carefully measured solutions that may include water, sugars, humectants like glycerin, and flavor compounds. These solutions help keep the tobacco from drying out, ensure even burning, and stabilize the product over time. The treated tobacco then rests in conditioning silos, allowing the additive to distribute evenly throughout the leaf material. Next comes cutting, where large sheets and strips of tobacco are transformed into the fine shreds used inside cigarettes. High-speed cutters slice the tobacco into narrow strands called cut filler. The width and length of these strands are critical. If they're too fine, the cigarette burns too fast. Too coarse and airflow is restricted. Laser sensors and vision systems measure strand size in real time, adjusting blade speed and spacing automatically. After cutting, the tobacco passes through dryers or coolers that fine-tune moisture content to precise targets, often within fractions of a percent. While the tobacco is being prepared, other parts of the cigarette are manufactured in parallel. Cigarette paper is produced from cellulose fibers and engineered to control burn rate, ash appearance, and smoke delivery. Some papers include microscopic perforations that dilute smoke with air during inhalation. Filters are made from cellulose acetate, a plastic-like material formed into long rods with thousands of tiny fibers. These fibers are bonded together and wrapped in plug wrap paper. The filter rods are cut into short segments sized to match individual cigarettes. Filter design, light including density and ventilation, plays a major role in draw resistance and smoke characteristics. Now comes the heart of the factory, the cigarette-making machines. These machines are among the fastest continuous manufacturing systems in the world. Prepared tobacco is fed into a forming section where it's evenly distributed onto a moving paper ribbon. The paper wraps around the tobacco, forming a continuous cigarette rod that's sealed with a thin line of adhesive. This rod can be produced at speeds exceeding 7,000 cigarettes per minute. Immediately after formation, the rod passes through cutting knives that slice it into precise lengths. At the same time, filter segments are aligned and attached. In many designs, 2 tobacco rods are joined to a double-length filter and then cut in half, creating 2 finished cigarettes in a single step. Adhesive systems bond the filter to the cigarette paper using tipping paper, the distinctive banded paper around the filter end. Cameras inspect alignment, length, and seal integrity at full speed. Any cigarette that fails inspection is automatically ejected. After formation, cigarettes move to conditioning chambers where temperature and humidity are stabilized. This prevents warping, cracking, or moisture loss before packaging. From there, they enter the packing line, another high-speed operation. Cigarettes are counted and arranged into precise groups, usually 20 per pack. Machines place them into foil liners designed to preserve freshness. The foil is folded and sealed tightly around the cigarettes, then inserted into printed cardboard packs. Each pack is glued shut, stamped with batch codes and tax markings, and inspected by vision systems to verify correct branding and warnings. Packs then move to cartoning machines that group multiple packs into cartons. Cartons are wrapped in clear film for tamper resistance and protection. From there, cartons are packed into cases and stacked on pallets by robotic systems. Throughout packaging, barcodes and tracking codes are applied, allowing every case to be traced back through the manufacturing process. This traceability is essential for regulatory compliance and quality assurance. Quality control runs continuously at every stage. Laboratories inside cigarette factories analyze tobacco moisture, blend composition, burn rate, paper permeability, filter ventilation, and draw resistance. Finished cigarettes are tested using smoking machines that simulate standardized puffing patterns. These machines measure parameters such as smoke volume, burn time, and consistency, not for consumer use but to ensure manufacturing stability and regulatory reporting. Visual inspections check paper seams, filter attachment, and pack integrity. Any deviation outside specification triggers immediate adjustments or halts production. Behind the scenes, environmental control is critical. Tobacco is highly sensitive to humidity and temperature. Factories maintain carefully controlled climates to prevent drying or mold growth. Air filtration systems capture tobacco dust, which is both a fire risk and a quality issue. Dust collection systems, explosion-proof motors, and strict housekeeping protocols keep operations safe. Logistics complete the journey. Finished cases are stored in climate-controlled warehouses before being distributed to regional centers. Transportation follows strict handling requirements to preserve product condition. Inventory systems manage shelf life, batch rotation, and regulatory documentation across borders. Because tobacco products are heavily regulated, factories maintain extensive records covering sourcing, processing, testing, and packaging. What makes cigarette manufacturing remarkable from an industrial perspective is its sheer speed and precision. A product made from agricultural leaves passes through curing, blending, chemical treatment, micron-level cutting, high-speed assembly, and automated packaging, all in a process refined to produce billions of identical units every year. The engineering challenges lie not just in making cigarettes, but in making them exactly the same, every time, at extraordinary scale. From a dry tobacco leaf harvested in a field to a sealed pack on a store shelf, the journey involves agriculture, chemistry, mechanical engineering, automation, and logistics working together in perfect synchronization. It's a process largely invisible to the public, yet it represents one of the most sophisticated examples of mass production in the modern world. And that is exactly how cigarettes are cured, blended, cut, formed, filtered, packaged, and prepared for distribution. A complex industrial system hidden behind one of the most familiar products on Earth. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the factories and systems behind everyday products. Firearms are some of the most precisely engineered mechanical devices in the world. Machines built to withstand extreme pressure, cycle with flawless reliability, and operate safely under punishing conditions. Yet few people ever see inside a modern gun plant, where steel billets, aluminum forgings, polymer granules, and precision-machined components come together under strict quality control. Behind every finished firearm is a factory ecosystem featuring CNC machining centers, automated forging lines, heat treatment furnaces, broaching machines, polymer injection presses, robotic measurement systems, and ballistic testing ranges. And today on The How Factory, we're going inside those facilities to see how firearms are manufactured at scale. From raw metal to fully assembled, rigorously tested products designed for decades of use. What looks like a simple tool in the hand is actually the result of thousands of machining operations, computer-guided measurements, and metallurgy techniques perfected over generations. The journey begins with raw materials. Firearm manufacturers order steel and aluminum in the form of billets, bars, or forgings. Critical parts, like barrels, slides, bolts, and frames, require alloys engineered for strength, corrosion resistance, and heat tolerance. Aluminum receivers start as forged blocks compressed under massive hydraulic presses. Steel components begin as bars or partially formed shapes, created in high-temperature furnaces and hammer forges. These heavy-duty forging operations align the metal's grain structure, making parts far stronger than if they were cut from raw stock. Each piece is inspected for cracks, voids, or imperfections, using ultrasonic scanners or magnetic particle testing. Only perfectly clean forgings move forward. From here, the heart of firearm manufacturing takes over: CNC machining. Multi-axis machining centers, some with robotic loading arms, clamp each forging or billet and carve it down with precision tools. Over hours or even days, cutters remove material to reveal highly detailed internal and external geometry. Slides receive precisely machined rails and surfaces. Frames are drilled, milled, and tapped for various components. Bolt carriers and locking parts are shaped to extremely tight tolerances, because alignment and timing between components determine a firearm's reliability and safety. Throughout machining, quality control probes measure surfaces at micron-level precision. If a tool wears or a cut drifts outside tolerance, the machine automatically compensates or pauses the operation. Barrel production is one of the most specialized processes in the plant. It begins with a cylindrical steel blank drilled, using deep-hole boring machines that slowly push long drill rods through the metal while flooding it with coolant. After drilling, a reamer enlarges and smooths the bore to a controlled diameter. Next comes rifling, the formation of spiral grooves that stabilize a bullet in flight. Factories use several non-instructional industrial methods. Broach rifling, where a long-toothed rod pulls grooves into the barrel. Button rifling, where a hard metal button is pushed or pulled through to form grooves by cold working. And hammer forging, where external hammers compress the barrel blank around an internal mandrel carrying the rifling pattern. Each method requires massive machines, hardened tooling, and exact metallurgy. After rifling, barrels are stress-relieved in heat treatment furnaces to stabilize the steel. Once machining is complete, nearly every critical metal component undergoes heat treatment. Furnaces precisely cycle parts through heating, quenching, and tempering stages to increase hardness and fatigue resistance. Parts like bolts, locking lugs, and sear components endure extreme stress during operation, so metallurgical consistency is critical for long-term durability. Heat treat ovens use inert atmospheres to prevent oxidation, and computer systems log temperatures and soak times for every batch. After heat treatment, parts are shot peened with steel or ceramic beads to improve fatigue strength and surface integrity. Surface finishing is another essential step. Depending on the model, components may receive bluing, parkerizing, anodizing, nitriding, Cerakote, or other finishes to enhance corrosion resistance and appearance. Before any finish is applied, parts pass through multi-stage cleaning lines, ultrasonic baths, degreasers, abrasive blasting cabinets, or vibratory tumblers. Robots apply coatings with uniform thickness, and curing ovens harden finishes to withstand years of wear. While metal parts are being machined, the polymer department produces grips, stocks, and polymer frames using injection molding machines. Polymer pellets are melted and injected into steel molds under high pressure. These molds form complex shapes complete with internal reinforcements, textured surfaces, and mounting points. After cooling, parts are ejected and automatically trimmed. Some polymer frames incorporate metal inserts that are molded in place, combining strength with weight reduction. Each molded piece undergoes dimensional inspection before moving to assembly. As components across the factory reach completion, they enter sub-assembly stations. Triggers, safeties, magazine catches, extractors, and other small mechanical parts are assembled using jigs that ensure alignment. Springs are inserted with automated feeders. Pins are pressed into place using pneumatic or hydraulic presses. Technicians follow strict documentation and testing protocols because these small parts play critical roles in timing and function. Sub-assemblies are inspected for spring tension, free movement, and surface finish. Next comes full assembly, the stage where the firearm actually takes shape. On a long assembly line or in modular work cells, technicians marry the major components: frame or receiver, slide or bolt, barrel, trigger assembly, magazine interface, and control levers. Workers follow standardized build procedures, and torque tools ensure screws or fasteners meet specification. Throughout assembly, gauges check clearances, travel distances, and mechanical engagement of safety systems. A single firearm may undergo dozens of checks before it even leaves the assembly bench. After assembly, firearms enter the testing stage. Every unit undergoes mechanical checks for cycling, dry function inspection, and measurement of critical safety mechanisms. Only after passing internal tests do they move to the ballistic test range. Here, each firearm is secured in a test fixture, not operated by hand, and fired remotely using proof loads that generate pressures far above normal. This extreme test validates barrel integrity, chamber strength, and safe function under stress. Technicians analyze spent cases, bolt face imprints, ejection patterns, and internal wear marks. If the firearm performs normally, it passes proof testing. Additional function testing follows using standard ammunition to confirm cycling reliability. Firearms that fail are sent back for diagnosis and rework. Once testing is complete, each firearm is cleaned, lubricated, and reassembled for final inspection. Serial numbers, model details, and compliance markings are engraved or laser etched. Quality inspectors check cosmetic finish, alignment, trigger feel, safety function, magazine fit, and general build quality. Only units meeting every requirement move on to packaging. Packaging is its own controlled process. Firearms are placed into custom-cut foam inserts or molded cases along with manuals, locks, and accessories required by regulation. Cases then travel to labeling stations where identification codes, barcodes, and shipping labels are applied. Warehouse automation sorts packaged firearms onto pallets bound for distributors, military customers, law enforcement agencies, sporting goods retailers, and international markets according to local laws. Behind all of this is an enormous documentation and compliance infrastructure. Modern gun plants track every component through serial-numbered batch systems and digital manufacturing records. Metallurgy data, torque logs, heat treat profiles, test results, and assembly steps are recorded to ensure traceability and safety compliance. Inspection labs perform metallographic analysis, hardness testing, dimensional metrology, and fatigue simulation. Factories must maintain strict security, controlled access, and regulatory oversight throughout the entire process. What makes firearm manufacturing remarkable is the combination of brute force industrial machinery and microscopic precision. A slide or bolt may endure explosive pressure, yet its surfaces must be polished to near mirror finish for reliable cycling. Barrels face thousands of high-temperature pressure pulses, yet their rifling geometry must remain perfectly uniform. Safety mechanisms must function flawlessly every time under every condition. These machines may appear rugged and simple from the outside, but their internal engineering is refined, exact, and deeply complex. And that is exactly how modern firearms are forged, machined, heat-treated, finished, assembled, tested, and certified. A blend of metallurgy, precision engineering, robotics, and strict quality control working together to produce some of the most precisely built mechanical systems on Earth. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines and systems behind everyday products. Toilet paper is one of the most essential everyday products on Earth. Soft, disposable, and used billions of times a day, yet almost no one ever thinks about the massive industrial system required to produce it. Behind every roll in a bathroom lies a highly engineered process involving recycled paper recovery, pulping chemistry, massive drying machines, precision embossing, high-speed winding, automated cutting, and non-stop packaging lines operating around the clock. What seems like a simple paper roll is actually the result of one of the largest and most efficient paper manufacturing operations in the modern world. And today on The How Factory, we're going inside the giant mills where toilet paper is transformed from recycled pulp into the soft, strong rolls shipped worldwide. The process begins far from the bathroom, at recycling centers and paper collection facilities. Large volumes of used paper, such as office paper, cardboard, and other clean paper waste, are collected and transported to tissue mills. Some toilet paper is also made from virgin wood pulp, but recycled fiber plays a major role in modern production. At the mill, incoming paper is inspected to remove contaminants like plastic, staples, tape, or food residue. Conveyor belts carry the paper through sorting systems that separate usable fiber from waste. This initial screening is critical because impurities can damage machinery or weaken the final product. Once sorted, the paper enters the pulping stage. Massive hydropulpers, giant tanks filled with warm water, churn the paper at high speed, breaking it down into individual cellulose fibers. Rotating blades and turbulence tear the paper apart, creating a slurry that resembles thick soup. During this process, additional cleaning systems remove ink, adhesives, and microscopic contaminants. Centrifugal cleaners spin the pulp so heavier particles fall away, while screens filter out unwanted debris. The goal is to recover clean, flexible fibers that can be reused to make soft tissue. After pulping, the fiber slurry undergoes de-inking and bleaching. Even recycled paper must be lightened and purified before becoming toilet paper. Air flotation systems inject air bubbles into the slurry, lifting ink particles to the surface where they are skimmed off. Chemical agents help detach ink from fibers without damaging them. Depending on the desired whiteness, the pulp may be bleached using oxygen-based or hydrogen peroxide systems. Modern mills avoid harsh chlorine processes, focusing instead on environmentally safer methods. At the end of this stage, the pulp is clean, bright, and ready for paper formation. And now comes one of the most impressive machines in the factory, the tissue paper machine. This machine can stretch hundreds of meters long and run at astonishing speeds. The cleaned pulp, now mostly water with only a few percent fiber, is pumped onto a moving wire screen called a forming fabric. As the slurry spreads across the screen, water drains away, leaving a thin mat of fibers. This mat is extremely fragile at first, so vacuum systems gently remove more water while supporting the sheet. The fibers begin bonding naturally, forming the structure of the paper. From the forming section, the wet paper sheet transfers onto a massive heated cylinder known as a Yankee dryer. This is where toilet paper gains its softness and bulk. The Yankee dryer is a giant steam-heated drum that dries the paper rapidly as it presses against the surface. A special adhesive holds the paper to the drum, while hot air hoods blast moisture away. As the paper dries, a doctor blade scrapes it off the drum in a process called creeping. This scraping action creates tiny folds and wrinkles in the paper, giving toilet paper its softness, stretch, and absorbency. Creping is a delicate balance. Too much, and the paper becomes weak. Too little, and it feels stiff. Once crept, the tissue paper is fully dry, but still incredibly thin. It moves through additional rollers that control thickness, tension, and texture. At this stage, plies are formed. Single-ply paper may move directly forward, while two-ply or three-ply products involve layering multiple sheets together. These layers are bonded using pressure or small amounts of adhesive at specific points. Multi-ply construction improves strength and comfort without making the paper feel heavy. Next comes embossing, a key step in toilet paper manufacturing. Embossing rollers press patterns into the layered tissue, creating decorative designs while increasing bulk and absorbency. These patterns also help the plies bond together more securely. Embossing requires precise alignment. If the rollers drift even slightly, the paper can tear or lose uniformity. Sensors and automated controls constantly adjust pressure and alignment to maintain consistent quality at high speed. After embossing, the continuous sheet of toilet paper moves to the winding section. Here, the paper is wound onto large cardboard tubes to form massive parent rolls. These parent rolls can be several meters wide and weigh thousands of kilograms. The winding tension must be carefully controlled. Too tight, and the paper becomes dense and rough. Too loose, and the rolls deform during cutting. Once complete, parent rolls are transferred to converting lines where they are turned into consumer-sized products. In the converting area, parent rolls are loaded onto unwind stands. The paper feeds into high-speed rewinding machines that cut, perforate, and wind the paper into individual toilet paper rolls. Perforation blades create the familiar tear lines at precise intervals. These perforations must be strong enough to hold the roll together, but weak enough to tear cleanly. Rewinders spin cardboard cores while wrapping the paper around them, building rolls to exact diameter and sheet count specifications. As rolls form, automatic knives cut them to length. The finished rolls pass through inspection systems that check diameter, weight, and sheet alignment. Any roll that fails to meet standards is removed automatically. High-end systems use cameras and sensors to detect defects like uneven winding, crushed cores, or misaligned perforations. Once cut, rolls move to packaging. Toilet paper packaging is designed for speed and efficiency rather than appearance alone. Rolls are grouped into packs, often 4, 6, 12, or even 24 rolls, using high-speed bundling machines. Plastic film wraps around the rolls, sealing them tightly while allowing some compression for shipping efficiency. Printed branding, product information, and barcodes are applied during wrapping. Some products use paper-based packaging as companies seek more sustainable options. After wrapping, packs are transferred to case packing systems. Robotic arms or automated loaders place packages into cardboard cases or stack them directly onto pallets. Palletizers arrange packs in stable configurations to prevent shifting during transport. Stretch wrap machines secure the pallets for shipping. Warehouse systems track every pallet's destination, batch number, and production time. Throughout the entire process, quality control never stops. Laboratories test paper softness, strength, absorbency, and disintegration behavior. Toilet paper must be strong enough to use, yet break down quickly in water to prevent plumbing issues. Samples are flushed and agitated in test systems that simulate real-world conditions. Fiber composition, moisture content, and ply bonding are continuously monitored. If any parameter drifts outside specification, adjustments are made immediately on the production line. Behind the scenes, toilet paper manufacturing is also heavily focused on efficiency and sustainability. Mills recycle water extensively, filtering and reusing it throughout the pulping and paper-making process. Heat from the Yankee dryer is recovered and reused. Waste fibers are captured and returned to the system. Sludge from de-inking is processed for energy recovery or responsible disposal. Modern mills aim to minimize environmental impact while producing enormous volumes of paper. What makes toilet paper manufacturing remarkable is the scale and speed at which it operates. Tissue machines run non-stop, producing kilometers of paper every hour. Converting lines can turn that paper into thousands of rolls per minute. All of this must happen with extreme consistency. Every roll must feel the same, tear the same, and dissolve the same no matter where it's purchased. From recycled paper fibers swirling in a pulper to soft embossed sheets wrapped around a cardboard core, the journey of toilet paper is a masterclass in industrial efficiency. It combines chemistry, mechanical engineering, automation, and material science to produce a product so familiar that most people never question how it's made. And that is exactly how toilet paper is cleaned, pulped, dried, creped, embossed, perforated, rolled, wrapped, and shipped. A massive industrial process hidden behind one of the most essential everyday products on Earth. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, factories, and systems behind everyday products. Artificial Christmas trees may look soft, festive, and simple once they're standing in living rooms, covered in lights and ornaments. But behind every tree is a massive industrial manufacturing process involving steel wire forming, PVC extrusion, injection molding, automated branch cutting, flame retardant treatment, color blending, hand assembly, quality inspection, and global logistics. What appears to be a seasonal decoration is actually the product of highly optimized mega factories capable of producing millions of identical trees every year with precise shape, durability, and safety standards. And today on The How Factory, we're going inside those factories to see exactly how artificial Christmas trees are manufactured. From raw plastic and steel wire to fully boxed trees shipped around the world. The process begins with raw materials. Artificial trees are primarily made from PVC plastic, polyethylene, steel wire, and injection molded polymers. PVC resin arrives at the factory in large bags or silos as fine white pellets or powder. These pellets are the base material for most traditional artificial needles. Meanwhile, steel wire, used to form branches and trunks, arrives in large coils weighing hundreds of kilograms. Different gauges of wire are used depending on whether the part will become a flexible branch tip, a strong branch spine, or the central trunk. Before production starts, materials are tested for flexibility, tensile strength, color consistency, and flame retardant performance because artificial trees must meet safety regulations in multiple countries. One of the most important early steps is PVC film production. PVC pellets are fed into large extrusion machines where they are heated until molten and pushed through flat dies to form thin sheets. These sheets are cooled on rollers and wound into large rolls. At this stage, pigments are added to the PVC to create different shades of green, and sometimes brown, to mimic natural needles and branch stems. Higher-end trees often use multiple green tones blended together to give a more realistic appearance. Flame retardant additives are mixed into the plastic so the finished tree resists ignition from lights or heat sources. Once the PVC film is produced, it moves to cutting machines. These machines slice the film into narrow strips, then cut those strips into thousands of tiny needle shapes per minute. The exact shape depends on the tree style. Flat needles, tapered needles, or fine needle cuts that resemble pine or fir trees. Cutting blades are extremely sharp and precisely aligned because even small defects can cause inconsistent needle density or weak attachment points. The cut needles fall into collection bins and are transported to the branch-making area. While needles are being prepared, steel wire is formed into branch cores. Wire straightening machines pull wire from coils and cut it into exact lengths. These lengths are then fed into branch-forming machines. In this step, two pieces of wire sandwich a bundle of PVC needles. The machine twists the wire tightly around the needles, locking them in place and forming a flexible artificial branch. This twisting process happens at high speed. Some machines can produce hundreds of branches per hour. The result is a dense, brush-like branch with needles radiating outward. Different branch sizes are produced for different tree levels. Shorter branches for the top, longer and stronger branches for the lower sections. For more realistic premium trees, factories use injection-molded polyethylene needles instead of cut PVC film. In this process, molten polyethylene is injected into steel molds shaped like real tree needles taken from actual pine or fir branches. These molded needles have three-dimensional texture, veins, and tapered tips. Once molded, the needles are stripped from runners, trimmed, and sometimes painted with multiple shades for realism. These molded tips are then attached to wire branches manually or semi-automatically, often combined with traditional PVC needles closer to the branch base. This hybrid construction creates trees that look realistic on the outside while remaining cost-effective to produce. At the same time, trunk sections are manufactured. The trunk is the backbone of the tree and must support the full weight of branches, decorations, and lights. Steel pipes or thick wire bundles are cut to length and welded or crimped together into sectional trunks. Many trees are designed to break down into 2 or 3 trunk sections for easier shipping and storage. Connection points are engineered to fit snugly while remaining easy for consumers to assemble. Hinges or hook systems are welded onto the trunk to hold branches. In hinge designs, branches are permanently attached to the trunk and fold down for storage. In hook-in designs, branches are inserted individually during setup. Once branches and trunk sections are ready, the process moves to assembly lines. And this is where automation meets human craftsmanship. Workers assemble trees in stages, starting from the bottom section. Branches are attached according to precise patterns that determine the final shape and fullness of the tree. Each row is spaced carefully so branches overlap naturally without leaving gaps. Assembly guides, jigs, and templates help workers maintain consistent spacing and angles. Even in highly automated factories, this step often involves human workers because visual judgment is critical to achieving a natural look. As the tree grows taller on the line, smaller branches are added toward the top. The tree's profile as narrow, full, slim, or wide is determined here. Quality inspectors monitor fullness, symmetry, and branch density continuously. If a tree appears uneven or sparse, adjustments are made immediately. Some factories use rotating platforms so inspectors can view the tree from all angles during assembly. For pre-lit artificial trees, another layer of complexity is added. Electrical wiring harnesses are integrated into the branches and trunk. LED light strings arrive pre-assembled with connectors designed to snap together automatically when trunk sections are joined. Workers route wires along branches, securing them discreetly so they're hidden by needles. Control modules and plugs are tested for electrical safety, brightness consistency, and color temperature. Burn-in tests power the lights for extended periods to identify early failures before the trees leave the factory. After assembly, trees move to shaping and finishing. Workers manually fluff branches, bending them outward to achieve the intended fullness. This step is crucial because branches are compressed during manufacturing and shipping. Factories train workers to shape branches in a standardized way so every tree looks similar when customers open the box. Higher-end trees may go through multiple shaping passes and inspections. Once shaped, trees enter the safety and quality testing phase. Samples from each production batch undergo flame retardant testing, where needles are exposed to open flame to ensure they self-extinguish. Structural tests check branch strength, trunk stability, and base connection integrity. Pull tests verify that needles and branches won't detach easily during handling. Electrical tests confirm insulation, grounding, and short-circuit protection for pre-lit models. Visual inspections check color consistency, needle density, and overall appearance. After approval, trees move to disassembly for packaging. Most trees are partially collapsed or separated into sections. Branches are folded upward tightly around the trunk, using compression machines or manual wrapping. Protective sleeves or plastic wrap prevent needles from bending permanently. Trunk sections, branches, and bases are grouped together with instruction manuals and hardware kits. Packaging is another industrial operation in itself. Cardboard boxes are printed, cut, folded, and glued on high-speed packaging lines. Trees are inserted into boxes using conveyor systems and guided chutes. Boxes are weighed to confirm all components are present. Barcodes, batch numbers, and tracking labels are applied for inventory and traceability. Finished boxes are sealed, stacked onto pallets, and wrapped in stretch film. Behind the scenes, logistics planning is constant. Artificial Christmas trees are seasonal products, so factories ramp up production months in advance. Warehouses store millions of boxed trees waiting for global distribution. Containers are loaded with precision to maximize space, and shipments are timed to reach retailers well before the holiday season. Inventory systems track models, sizes, lighting options, and destination markets. Many factories ship directly to distribution centers in North America, Europe, and Asia. Environmental considerations also play a growing role. Manufacturers work to reduce PVC waste by recycling offcuts back into extrusion lines. Steel wire scraps are collected and recycled. Energy-efficient motors, LED lighting, and improved molding processes reduce power consumption. Some companies are experimenting with bio-based plastics and more recyclable materials to lower environmental impact. What makes artificial Christmas tree manufacturing remarkable is the balance between mass production and visual realism. These factories produce millions of nearly identical trees, yet each one must look natural, symmetrical, safe, and festive. The process blends plastics engineering, metal forming, electrical assembly, manual craftsmanship, and logistics coordination, all tuned for a single season that defines the product's purpose. And that is exactly how artificial Christmas trees are extruded, cut, twisted, molded, assembled, wired, shaped, tested, boxed, and shipped from mega factories to homes around the world. A fascinating combination of industrial efficiency and holiday tradition hidden behind one of the most recognizable seasonal products on Earth. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines and systems behind everyday products. KFC chicken might seem simple when it arrives hot and crispy in a red and white bucket. But behind every piece is a vast, tightly controlled industrial food system that begins long before a restaurant fryer ever turns on. From large-scale poultry processing plants to precision seasoning systems, refrigerated logistics networks, and highly standardized restaurant kitchens, KFC's chicken is the result of one of the most coordinated fast food supply chains in the world. And today on The How Factory, we're going deep inside that system, following the journey of KFC chicken from the processing plant all the way to the restaurant kitchen. What looks like comfort food is actually the outcome of strict food safety engineering, cold chain logistics, high-volume preparation, and carefully controlled cooking methods designed to deliver the same taste and texture across thousands of locations worldwide. The journey begins at poultry processing facilities that supply KFC-approved chicken. These plants operate under strict animal welfare, food safety, and quality standards set by both regulators and the brand itself. Chickens arrive from farms in climate-controlled transport vehicles to minimize stress and maintain meat quality. At the plant, birds move through automated processing lines designed to handle thousands per hour. The process is highly regulated and monitored, with every stage designed to ensure cleanliness, consistency, and safety. After processing, the chicken is chilled rapidly to prevent bacterial growth, then graded by size and cut type. KFC uses specific portions: drumsticks, thighs, breasts, wings, and fillets. each trimmed to precise specifications so cooking times remain consistent later in the restaurant. Once cut and inspected, the chicken is thoroughly washed and immediately cooled. Temperature control is critical here. Sensors ensure the meat stays within safe ranges at all times. The chicken then enters a marination stage. While KFC's exact seasoning blend is famously secret, the early-stage marinade typically includes water, salt, and functional ingredients that improve juiciness and texture. Large stainless steel tumblers rotate the chicken pieces gently, allowing the marinade to penetrate evenly. This step helps ensure that the meat remains tender after frying, and that seasoning is distributed consistently throughout each piece. After marination, the chicken is packaged for transport. Portions are weighed automatically and sealed into food-grade bags or trays. Some products are shipped fresh under refrigeration, while others are frozen depending on region, distance, and supply chain design. Blast freezers rapidly reduce temperature to lock in quality when freezing is used. Each package is labeled with batch numbers, production dates, and traceability codes, so every piece of chicken can be tracked from plant to restaurant. Before leaving the facility, samples from each batch undergo microbiological testing, moisture analysis, and visual inspection. Only approved batches enter the distribution network. From the processing plant, the chicken moves into cold chain logistics. Refrigerated trucks transport the product to regional distribution centers. These facilities act as hubs, storing chicken at tightly controlled temperatures and redistributing it to individual restaurants. Warehouse management systems track inventory in real time, ensuring first-in, first-out rotation to maintain freshness. Any break in the cold chain can compromise safety, so trucks, warehouses, and loading docks are all monitored by temperature sensors with automatic alerts. When the chicken arrives at a KFC restaurant, the process enters its final and most visible stage. Restaurant kitchens are designed for consistency, speed, and safety, rather than traditional cooking flexibility. Staff receive the chicken either chilled or frozen. Frozen products are thawed in dedicated refrigeration units over a controlled period to prevent temperature shock. Raw chicken is never left at room temperature. Every movement follows standardized procedures designed to minimize handling and prevent cross-contamination. Preparation begins with breading, one of the most iconic steps in KFC's process. In the kitchen, staff work at dedicated breading stations. The chicken is first inspected to ensure correct size and quality, then coated in a pre-mix solution that helps the flour adhere. Next comes the flouring stage. KFC's seasoned flour, containing the famous blend of herbs and spices, is mixed fresh in-store according to strict ratios. Chicken pieces are rolled, pressed, and flipped in the flour so every surface is fully coated. The pressure applied during breading is important. It helps create the craggy, crispy texture that defines KFC's fried chicken. Any excess flour is shaken off before cooking. Once breaded, the chicken moves immediately to the fryer. Timing is critical. Letting breaded chicken sit too long can affect coating, adhesion, and texture. KFC uses pressure fryers for most bone-in chicken. These machines look similar to industrial pressure cookers and are a key part of the brand's signature result. The fryer is filled with oil heated to a precise temperature. When the chicken is lowered into the fryer, the lid seals shut and pressure builds inside. This allows the chicken to cook faster while retaining moisture, producing juicy meat with a crisp exterior. Cooking times and pressures are digitally controlled, removing guesswork and ensuring consistency across locations. Boneless products and some specialty items may use open fryers instead. These operate at carefully regulated temperatures and cooking times designed for thinner cuts. In all cases, oil quality is constantly monitored. Restaurants filter oil regularly and replace it according to strict schedules. Degraded oil affects flavor, color, and food safety, so this step is closely controlled. When cooking is complete, the fryer automatically releases pressure and the chicken is lifted out to drain. Each piece is visually inspected by staff to ensure proper color and coating. The chicken then moves to heated holding cabinets. These cabinets maintain temperature and humidity to keep the chicken hot and crispy without drying it out. Holding times are strictly limited. If chicken exceeds its holding window, it must be discarded. This ensures customers always receive freshly cooked product rather than food that has been sitting too long. Meanwhile, quality checks continue behind the scenes. Managers perform routine checks on cooking temperatures, oil condition, breading consistency, and holding times. Digital systems log fryer performance and alert staff if anything falls outside specification. Food safety audits, both internal and external, regularly inspect restaurants to ensure compliance with hygiene standards. Gloves, hand-washing protocols, and equipment sanitation are enforced continuously throughout the day. While the chicken itself is the star, the surrounding systems are just as important. Packaging materials are designed to vent steam so the coating stays crispy. Boxes, buckets, and liners are engineered to retain heat without trapping moisture. Even the way chicken is stacked inside a bucket is standardized to prevent crushing and sogginess. Every detail is tested repeatedly before being rolled out across thousands of restaurants. What makes KFC's system remarkable is how it balances industrial-scale consistency with in-restaurant preparation. Unlike fully pre-cooked fast food, KFC chicken is finished on-site. This requires training, discipline, and equipment designed to remove variability from human cooking. Pressure fryers, digital timers, standardized breading methods, and controlled supply chains all work together, so a piece of chicken tastes the same whether it's served in a small town or a major city on the other side of the world. Behind the scenes, supply chain planners forecast demand weeks in advance. Processing plants adjust output based on seasonal trends. Distribution centers coordinate deliveries, so restaurants receive the right mix of cuts. Equipment manufacturers design fryers and holding cabinets specifically for KFC's requirements. Food scientists test coatings, marinades, and cooking profiles under hundreds of conditions. All of this happens so the final experience feels simple and familiar to the customer. From a raw bird at a processing plant to a hot piece of fried chicken in a restaurant, the journey involves strict temperature control, industrial marination, standardized breading, pressure frying, and real-time quality monitoring. It's a system built not just for speed, but for safety, consistency, and scale, serving millions of customers every day without compromising reliability. And that is exactly how KFC chicken is processed, marinated, breaded, and pressure fried, held, and served. A carefully engineered combination of food science, industrial processing, cold chain logistics, and standardized kitchen execution working together behind one of the world's most recognizable meals. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, systems, and factories behind everyday products. Pencils are one of the most familiar tools in human history. Simple, lightweight, and inexpensive. Yet behind every perfectly sharpened tip lies a surprisingly complex industrial process involving forestry management, precision milling, graphite chemistry, high-temperature firing, automated assembly lines, finishing systems, and quality control refined over centuries. What appears to be nothing more than wood and graphite is actually the product of one of the most optimized manufacturing systems ever developed, capable of producing millions of identical writing instruments every single day. And today on The How Factory, we're stepping inside modern pencil factories to see exactly how pencils are made. From raw wood and powdered minerals to smooth, balanced pencils ready to write straight out of the box. The journey begins not in a factory, but in managed forests. Pencil manufacturers rely heavily on specific types of wood, most commonly incense cedar, basswood, or gelutong. These woods are chosen for their straight grain, softness, low splintering tendency, and ability to be sharpened cleanly without cracking. Trees are harvested sustainably, debarked, and cut into logs before being transported to lumber mills. At the mill, logs are sawn into thin rectangular boards called slats. These slats are the future bodies of pencils. Each slat is carefully cut to precise dimensions, usually long enough to make several pencils at once. Moisture content is critical, so the slats are kiln-dried to remove excess water and stabilize the wood. If the wood is too wet, it will warp, too dry, and it will crack during machining. Once dried, the slats move into planing and milling lines where their surfaces are smoothed and thickness is standardized. Automated scanners inspect the wood for knots, cracks, or defects. imperfect slats are rejected or repurposed. The remaining slats are then grooved, one of the most important woodworking steps in pencil production. CNC milling machines carve a series of long, evenly spaced grooves down the length of each slat. These grooves will hold the pencil lead, which is not actually lead at all, but graphite. The grooves must be perfectly aligned and uniform. Even slight variations can affect how the pencil writes or how easily it sharpens. While wood preparation is underway, the factory is also producing the pencil core, the writing center often called lead. Pencil cores are made from a carefully controlled mixture of graphite powder and clay. Graphite provides darkness and smoothness while clay controls hardness. By adjusting the ratio of graphite to clay, manufacturers create different grades, from soft, dark pencils to hard, light ones. The raw graphite and clay are first ground into fine powders and blended in large mixers until perfectly uniform. Water is then added to form a thick paste. This paste is fed into extrusion machines that push it through small dies, forming long, thin rods, the pencil leads. These fragile rods are cut to length and laid carefully onto trays. At this stage, they are still soft and weak. To gain strength, they must be fired. The leads enter high-temperature kilns where they are baked at temperatures exceeding 1,000 degrees Celsius. This firing process hardens the clay, bonds the graphite structure, and gives the lead its final strength and writing properties. After firing, the leads are cooled slowly to prevent cracking, then dipped in wax or oil baths. This final treatment improves smoothness and reduces friction during writing. Now the wood and lead come together. In the assembly area, a slat with grooves is placed onto a conveyor. Automated machines place a fired graphite rod into each groove. A second slat, without grooves, is coated with industrial adhesive and pressed on top, sandwiching the leads between the two pieces of wood. The result is a pencil sandwich, often containing 6 to 10 pencils bonded together in a single block. Hydraulic presses apply uniform pressure to ensure strong adhesion. The glued blocks are then cured, allowing the adhesive to fully set. Once cured, the blocks move to shaping machines. High-speed cutters slice the block into individual pencils while simultaneously shaping them. Depending on the design, pencils may be round, hexagonal, or triangular. Hexagonal shapes are especially popular because they prevent pencils from rolling off desks. These shaping machines operate with incredible precision, producing thousands of perfectly uniform pencils per hour. As the pencils emerge, they are sanded smooth to remove tool marks and sharp edges. At this stage, the pencils are still bare wood. They now move into finishing lines where appearance and durability are added. First, pencils are sealed with a base coat to protect the wood. Then they pass through multiple painting stations. Most pencils receive several coats of paint, often applied by curtain coaters or spray systems, with drying ovens between each layer. This creates a smooth, durable finish that resists chipping. Color consistency is tightly controlled, especially for branded pencils. Some pencils receive multiple colors, stripes, or decorative patterns, which are applied using precision rollers or printing machines. After painting, many pencils receive stamping or printing. Machines apply brand names, logos, grade markings, and decorative text using hot foil stamping or ink printing. These markings must be perfectly aligned and legible. Vision systems inspect each pencil for print clarity and placement. Any pencil with smudged or missing text is rejected automatically. Next comes ferrule and eraser attachment for pencils designed with erasers. Ferrules, the small metal bands, are stamped from aluminum or brass and formed into short cylinders. Erasers are made separately from rubber or synthetic compounds, molded into long strips and cut into small plugs. Automated assembly machines slide a ferrule onto the end of the pencil, insert the eraser, and crimp the ferrule tightly to hold everything in place. The crimp must be firm enough to prevent loosening, but not so tight that it cracks the wood. With the pencil fully assembled, attention turns to sharpening, one of the most iconic steps. In many factories, pencils are pre-sharpened before packaging. High-speed sharpening machines hold pencils at precise angles and grind the wood away to expose the graphite core. The angle and length of the sharpened tip are carefully controlled to ensure strength and smooth writing. Dust extraction systems capture wood shavings and graphite particles, which are recycled or reused. After sharpening, the tips are inspected to ensure the graphite is centered and unbroken. A centered core is critical. Off-center leads break easily during use. Quality control runs continuously throughout the factory. Samples from every production batch are tested for writing performance, break resistance, sharpening behavior, paint adhesion, and eraser effectiveness. Writing tests check darkness, smoothness, and consistency. Drop tests ensure leads don't shatter inside the wood. Sharpening tests confirm that the pencil forms clean shavings instead of splintering. Only pencils that pass all tests move on. Finished pencils now move to packaging lines. Depending on the product, pencils may be packed loose, bundled with bands, placed into cardboard boxes, or sealed in blister packs. Automated counting machines ensure the correct number of pencils per package. Boxes are folded, filled, and sealed at high speed. Barcodes, batch numbers, and country of origin markings are printed for tracking and compliance. Behind the scenes, pencil factories operate with impressive efficiency. Wood waste from shaping is collected and often reused as fuel or compressed into pellets. Graphite dust is captured and recycled. Water used in lead production and painting is filtered and reused in closed-loop systems. Many factories now incorporate sustainability programs, using certified wood sources and reducing solvent-based coatings. What makes pencil manufacturing so remarkable is how much precision goes into such a simple object. A pencil must feel balanced in the hand, sharpen cleanly, write smoothly, resist breakage, erase cleanly, and look consistent, all while costing only a small amount to produce. Achieving that balance requires tight control over materials, machines, and processes refined over generations. From forest-grown wood to fired graphite cores, from grooved slats to painted barrels, from ferrule crimping to perfectly sharp tips, every pencil is the result of careful engineering and industrial craftsmanship. It's a quiet process hidden behind an everyday object that billions of people use without a second thought. And that is exactly how pencils are made. Harvested, milled, filled, shaped, painted, stamped, sharpened, tested, and packaged into one of the most reliable tools ever created. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, materials, and factories behind everyday products. Thanks for watching. New videos every day. In a quiet suburb, a robotic arm hums softly as it moves back and forth, layer by layer building the walls of a brand new home. There are no bricks, no carpenters, no weeks of construction noise, just precision, speed, and science. Within days, what once was an empty lot becomes a finished house, solid, sustainable, and ready to live in. Welcome to the How Factory, where we explore how 3D printed homes are built in days, changing everything we know about construction. For centuries, building a house meant the same thing: bricks, cement, scaffolding, sweat, and time. Traditional construction takes months, sometimes years, and is vulnerable to labor shortages, weather delays, and high material costs. But today, a new revolution is taking shape. One that swaps hammers and nails for robotics and software. 3D printing, once limited to small plastic prototypes, has scaled up to the world of architecture, where machines can now print entire homes from the ground up. And it all starts not with blueprints on paper, but with digital design. Every 3D printed home begins inside a computer. Architects and engineers model the entire structure in 3D software, from the foundation to the roofline, tweaking every wall, window, and corner. This digital plan becomes the house's DNA, telling the printer exactly where to place each line of material. Specialized software slices the model into hundreds or thousands of layers, each representing a few millimeters of height. These layers act like roadmaps for the printer's nozzle, guiding it as it extrudes a continuous stream of custom concrete. The result: perfect precision, no wasted motion, and virtually zero human error. Once the file is ready, the job site becomes a lab of innovation. Instead of cranes and bricklayers, a massive robotic printer is brought in, often mounted on rails or set up with a giant gantry system that can move in 3 axes: left to right, forward and back, up and down. Some printers even sit on tracks and crawl around the site autonomously. The print material isn't ordinary cement. It's a specially formulated concrete mix that's strong, fast-drying, and flowable enough to be squeezed through a nozzle like toothpaste. This mixture includes fine aggregates, water, binding agents, and sometimes recycled or biodegradable materials. The key ingredient is its chemistry. It must harden quickly to support each new layer, but not so fast that it clogs the printer. When printing begins, the robot moves with quiet precision, guided by GPS and sensors. It lays down the first layer of concrete to form the base. Within minutes, the second layer is added directly on top. Slowly, the walls begin to rise. Curved, straight, and complex shapes that would be difficult or impossible to make by hand. Unlike traditional bricklaying, where each piece must be placed and aligned manually, the printer never tires, never slows down, and never misaligns a wall. It can work 24 hours a day if needed, often printing an entire single-story home in less than 48 hours. The structure grows like a living sculpture, the pattern of each layer visible like rings in a tree trunk. A visual reminder that this home was made by a machine. As the walls take shape, teams monitor the process using cameras, sensors, and drones. They measure temperature, humidity, and curing times to make sure the concrete sets correctly. Some advanced systems use AI to adjust speed, pressure, or mix consistency in real time. If rain or wind threatens to interrupt printing, the system can pause safely and resume later without losing accuracy. The robot becomes a construction crew, architect, and quality inspector, all in one. Inside the freshly printed walls, space is left for wiring, plumbing, and insulation. Once the print is complete, human builders return to install windows, doors, and roofing. It's a perfect partnership. Machines build the bones, humans handle the details. The benefits are massive. 3D printed homes can reduce construction waste by up to 70% because there are no offcuts, broken bricks, or extra materials. They can use less water and fewer resources overall, while producing structures that are both strong and sustainable. The speed is even more astonishing. In the time it takes to pour a traditional foundation, a 3D printer can build the entire frame of a house. That means homes can be built faster, cheaper, and with fewer workers. A major breakthrough for countries facing housing shortages. In parts of the world where affordable housing is scarce, this technology could be life-changing. Entire communities of 3D printed homes are already being built in Mexico, the United States, and Africa, offering safe, durable homes for families who could never afford traditional construction. Take Icon, a Texas-based company leading the charge. Their printers, called Vulcan, can build a 2,000-square-foot home in under 3 days using a proprietary concrete called lavacrete, durable enough to withstand storms, earthquakes, and time. Meanwhile, in Europe, companies like Cobod and Wasp are building multi-story 3D printed homes, schools, and offices using locally sourced materials and even clay-based mixes. In Dubai, an entire government building has been printed, the world's largest 3D printed structure to date. The process is fast, precise, and repeatable. Once one design is perfected, it can be printed again anywhere on Earth with just a click. But what makes 3D printing so revolutionary isn't just speed, it's freedom. Traditional construction relies on straight lines and right angles because they're easy to measure and cut. 3D printing, however, allows architects to experiment with curves, organic shapes, and flowing designs that mimic nature. Walls can curve, twist, or blend seamlessly into furniture or staircases. Homes can be printed to fit local climates, reducing the need for air conditioning or heating. Even insulation can be printed directly into the walls, reducing the need for extra materials. It's a completely new way to think about architecture. Not assembling buildings, but growing them layer by layer. Of course, challenges remain. The technology is still young and printers are expensive. Each mix of 3D concrete must be tested for local conditions, Building codes, safety standards, and permits often lag behind innovation. Electrical and plumbing systems still require human installation, and large-scale printing demands stable weather and flat terrain. But with every project, these obstacles shrink. New printers are becoming faster, cheaper, and more versatile. Some can even print multi-material structures combining concrete with carbon fiber or insulation foam in the same pass. Researchers are experimenting with 3D printing in space, using lunar dust to build habitats for future astronauts. What started as an experiment is quickly becoming a cornerstone of the construction industry. The sustainability potential is staggering. Construction is responsible for nearly 40% of global CO2 emissions, but 3D printing can dramatically reduce that footprint. By using recycled aggregates, bio-based materials, or even local soil, printed buildings can be carbon neutral or close to it. Some printers use solar-powered systems and on-site mixing units, eliminating the need for diesel generators or long supply chains. 3D printing also makes housing more resilient. Walls are seamless, reducing weak points that can crack or leak. The result is a home that lasts longer, costs less, and leaves a smaller environmental mark. After printing, finishing touches come fast. Roofs are assembled and sealed, windows installed, and interiors painted. Many projects use modular roofs and prefabricated electrical systems that snap into place. Because the walls are already smooth and precise, interior finishing is easier and faster than traditional plastering or drywall. Within a week, a once-empty field transforms into a livable neighborhood, something that used to take months or even years. The first time a family walks into a 3D printed home, it doesn't just feel modern, it feels like a glimpse of the future. And perhaps that's what makes 3D printed housing so powerful. It's not just about speed or cost, it's about possibility. Imagine disaster zones where entire villages could be rebuilt within days after a hurricane. Imagine affordable housing printed directly on site in developing nations. Imagine Mars colonies built by autonomous printers using Martian soil. Every advancement brings us closer to a world where housing is abundant, sustainable, and customized for every need. As 3D printing expands, it's merging with other technologies like AI design, robotics, and smart home systems. Future houses might self-diagnose cracks, print their own repairs, or adjust their structure for temperature and light. The idea of a living building is no longer science fiction. What began as a curiosity in labs has become a global movement, one that could redefine cities, economies, and human life itself. So the next time you see a robotic arm extruding gray lines of concrete under the sun, remember that you're not just watching construction, you're watching evolution. A process that once took months now happens in days. A dream that once required thousands of workers can now be achieved by a single machine and a digital file. It's efficiency, creativity, and sustainability fused into one. From digital design to final inspection, 3D printed homes prove that the future of construction isn't just faster, it's smarter. Every wall printed is a layer of innovation. Every foundation a step toward a new world where anyone, anywhere, can have a safe, affordable home. That's how 3D printed homes are built. In days, not months. Thanks for watching The How Factory, where we uncover how the world really works. Don't forget to like, subscribe, and stay tuned for more stories of technology, design, and human ingenuity shaping the future, one layer at a time. Gold bars are among the most valuable objects ever produced by human industry. Compact blocks of refined metal that represent wealth, stability, and trust across global markets. Yet behind every gleaming bar locked inside a vault lies one of the most tightly controlled and technically demanding manufacturing processes in the world. Gold refining and bar production combines extreme heat, chemical separation, precision casting, microscopic purity testing, robotic handling, and security protocols rivaling those of military facilities. What appears to be a simple rectangular bar is actually the final product of a long journey that begins with impure raw gold and ends with a certified asset traded between central banks, bullion dealers, and investors. And today on the How Factory, we're going inside secure vault refineries to see exactly how gold bars are refined, cast, stamped, tested, and sealed under constant surveillance. The journey begins with raw gold feedstock, which rarely arrives in pure form. Gold enters refineries as doré bars from mines, recycled jewelry, electronic waste, industrial scrap, or old bullion melted down for re-refining. Doré bars, semi-refined gold from mining operations, typically contain between 60 and 95% gold, with the remainder made up of silver, copper, zinc, and trace metals. These bars arrive under armed transport and strict documentation. Every shipment is weighed, sampled, logged, and sealed before processing begins. From the moment gold enters the facility, it is tracked continuously through digital inventory systems, cameras, and access-controlled zones. The first major stage is melting. Raw gold material is transferred into high-temperature induction furnaces or gas-fired crucible furnaces capable of reaching temperatures above 1,100 degrees Celsius. Inside ceramic or graphite crucibles, gold melts into a glowing liquid metal. Fluxes, specialized chemical compounds, are added to bind with impurities and separate them from the molten gold. These fluxes help draw unwanted elements to the surface as slag, which can later be removed. During melting, technicians take small samples using vacuum samplers or dip rods. These samples are cooled and sent to on-site laboratories for preliminary analysis to determine the exact composition of the melt. Once melted and homogenized, the gold moves into refining, the step that transforms impure metal into investment-grade bullion. Large refineries typically use either the Miller process, the Wohlwill process, or a combination of both. In the Miller process, chlorine gas is bubbled through molten gold. The chlorine reacts with base metals and silver, forming chlorides that rise to the surface and are skimmed off, leaving behind gold that is typically around 99.5% pure. This method is fast and efficient, making it ideal for bulk processing. However, for gold that must meet the highest purity standards, 99.99% or higher, further refinement is required. That's where the Wohlwill process comes in. In this method, gold is refined using electrolysis. Gold from the Miller process is cast into anodes and placed into electrolyte baths containing hydrochloric acid and gold chloride. When electric current passes through the solution, pure gold dissolves from the anode and deposits onto cathodes as ultra-pure metal. Impurities fall away as sludge, which is later processed separately to recover precious metals like platinum or palladium. This process is slow, energy-intensive, and extremely precise, but it produces gold pure enough for central banks and investment bars. Throughout refining, chemical concentrations, current density, temperature, and deposition rates are monitored constantly by automated systems. After refining, the pure gold is ready to be cast into bars. The molten metal is transferred from furnaces into casting stations located inside reinforced access-restricted rooms. For large bars, such as standard 400-ounce London Good delivery bars, refineries use gravity casting. Molten gold is poured carefully into preheated graphite or cast iron molds. These molds are designed to exact dimensions and are coated to prevent sticking. As the gold cools, it contracts slightly, forming the familiar trapezoidal shape. Cooling rates are carefully controlled to prevent internal stress or cracking. Once solidified, the bars are removed from molds using tongs or robotic arms and placed onto cooling racks. Smaller investment bars, such as 1 kilogram or 1 ounce bars, are often produced using continuous casting or minting methods. In continuous casting, molten gold is poured into long molds and then cut into uniform segments. In minting, refined gold is first cast into flat strips, rolled to precise thickness, and punched into blanks. These blanks are then stamped under enormous hydraulic presses to create perfectly uniform bars with sharp edges and smooth surfaces. Minted bars offer a more polished appearance and tighter weight tolerances, making them popular with retail investors. Once cast or minted, every bar undergoes finishing. Rough edges are ground smooth, surfaces are brushed or polished, and excess material is removed to bring each bar within extremely tight weight tolerances. Even fractions of a gram matter when dealing with precious metals. Bars are weighed repeatedly on calibrated scales, certified to international standards. Any bar outside specification is remelted and recast. Nothing leaves the refinery unless it meets exact dimensional and weight requirements. Next comes assaying, the process of verifying purity. This is one of the most critical steps in gold bar production. Samples are taken from each batch and analyzed using multiple methods. Fire assay, one of the oldest and most accurate techniques, involves melting a sample with lead and fluxes, separating gold from other metals and measuring the result with extraordinary precision. Modern refineries also use X-ray fluorescence spectroscopy and inductively coupled plasma analysis to confirm purity down to parts per million. Results are logged digitally and tied to specific bar serial numbers. If any discrepancy is detected, the entire batch is quarantined for investigation. After purity is confirmed, bars move to stamping and marking. Heavy stamping presses imprint each bar with essential information: refinery name, purity level, weight, year of manufacture, and a unique serial number. For large bars, these markings are often applied while the bar is still warm to ensure deep, permanent impressions. Smaller minted bars may receive laser engraving for cleaner, more precise markings. These identifiers allow each bar to be traced back through the refinery's records, ensuring authenticity and compliance with global bullion standards. At this stage, bars may also receive security features. Some refineries apply micro-engraved marks, holographic seals, or embedded tracking technologies for anti-counterfeiting purposes. These features help protect against fraud in secondary markets. Once marked, bars undergo a final visual inspection to ensure markings are clear, surfaces are free of defects, and edges are intact. The next phase is vaulting. Finished bars are transferred into high-security vault areas within the refinery. These vaults are constructed with reinforced concrete, steel doors, biometric access controls, and round-the-clock surveillance. Bars are stacked on pallets or stored in numbered racks according to customer, batch, or destination. Inventory systems track every movement in real time. Some bars may remain in the vault for years as part of long-term storage agreements, while others are prepared for immediate shipment. Before shipping, bars are sealed and documented. Export bars are packed into tamper-evident containers, often under the supervision of independent auditors. Weight lists, assay certificates, and chain of custody documents accompany every shipment. Armed security teams escort gold shipments to airports, banks, or distribution centers. Even during transport, temperature, shock, and location may be monitored to ensure integrity. Behind all of this is an extraordinary level of security and compliance. Gold refineries operate under strict national and international regulations designed to prevent theft, money laundering, and illicit sourcing. Audits are frequent. Cameras cover nearly every square meter of production space. Access to refining areas is limited and logged. Employees undergo background checks and training. Waste streams, some including slag, dust, and wastewater, are processed to recover any remaining precious metal before disposal. Environmental controls are equally important. Refining gold involves chemicals, high energy use, and metal residues. Modern refineries use closed-loop water systems, advanced filtration, and chemical recovery units to minimize environmental impact. Slag and byproducts are recycled or treated according to strict environmental standards. Even air inside refining rooms is filtered to capture microscopic gold particles. What makes gold bar manufacturing so remarkable is the contrast between scale and precision. These facilities handle tons of molten metal worth billions of dollars, yet measurements are made down to thousandths of a gram. Furnaces roar at extreme temperatures, yet purity is controlled at the atomic level. Security is absolute, but the process must flow continuously and efficiently. Every bar represents not just metal, but trust. Trust in the refinery, in the assay, and in the systems that guarantee authenticity. From impure doré bars to mirror-finished bullion stamped with serial numbers, the journey of a gold bar is a fusion of chemistry, metallurgy, automation, and security engineering. It's a process refined over centuries and perfected with modern technology, ensuring that when a gold bar enters a vault, its value is unquestioned anywhere on Earth. And that is exactly how gold bars are refined cast, stamped, tested, secured, and stored inside high-security vault factories, a hidden world of extreme precision and control behind one of humanity's most enduring symbols of value. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, systems, and factories behind the world's most fascinating products. Gasoline is one of the most critical fuels powering the modern world, moving cars, trucks, motorcycles, and machinery across continents every single day. Yet few people ever see the vast industrial system required to transform thick, black crude oil into the clear, highly refined fuel pumped into vehicles. Behind every gallon of gasoline lies one of the most complex chemical manufacturing operations on Earth, involving massive distillation towers, extreme heat, high-pressure reactors, precision blending systems, continuous laboratory testing, and non-stop safety monitoring. What appears to be a simple liquid is actually the final product of dozens of tightly controlled processes working together inside enormous oil refineries. And today on The How Factory, we're going step by step inside modern refineries to see exactly how gasoline is made from crude oil, from underground extraction to finished fuel ready for distribution. The journey begins with crude oil, a naturally occurring mixture of hydrocarbons formed over millions of years beneath the Earth's surface. Crude oil is extracted through drilling operations on land and offshore, then transported to refineries by pipelines, ships, or rail. When crude oil arrives at a refinery, it is anything but uniform. Different crude sources vary widely in thickness, sulfur content, and chemical makeup. Before processing begins, samples are taken and analyzed to determine the crude's composition. This information is critical because refining parameters must be adjusted depending on whether the crude is light or heavy, sweet or sour. Once approved, crude oil enters the refinery and is pre-treated. The first major step is desalting, a critical process that removes salt, water, and sediment. Crude oil is mixed with fresh water and passed through electrostatic separators that cause water droplets to merge and fall out, carrying salts and impurities with them. Removing salt is essential because salt can corrode equipment and poison catalysts used later in refining. After desalting, the crude oil is heated in large furnaces to temperatures exceeding 350 degrees Celsius, preparing it for separation. The heated crude oil then enters the atmospheric distillation unit, the heart of the refinery. This towering steel column, often over 40 meters tall, separates crude oil into different fractions based on boiling point. As the hot crude enters the base of the tower, it begins to vaporize. Lighter hydrocarbons rise upward, while heavier components fall downward. Inside the column, trays and packing materials help control vapor flow and condensation. At various heights, different products are drawn off. Gases at the top, followed by gasoline-range hydrocarbons, kerosene, diesel, and heavier oils. This process does not chemically change the oil, and it simply separates it. The fraction that will eventually become gasoline is called naphtha. However, straight-run naphtha from distillation is not suitable for modern engines. It lacks the proper volatility and octane rating required for efficient combustion. To transform it into usable gasoline, it must undergo several additional refining processes that rearrange its molecular structure. One of the first upgrading steps is catalytic reforming. In this process, naphtha is sent into high-pressure reactors containing platinum-based catalyst. Under temperatures around 500 degrees Celsius, the hydrocarbon molecules are reshaped into more complex structures. This increases the octane rating, allowing gasoline to burn smoothly without engine knocking. Reforming also produces hydrogen, which is captured and reused in other refinery processes. The output of this unit is a high-octane blending component essential for gasoline production. Another critical process is fluid catalytic cracking, often referred to as FCC. Heavy hydrocarbon fractions that are too large for gasoline use are fed into FCC units where they are exposed to extreme heat and powdered catalysts. The molecules crack into smaller, lighter hydrocarbons suitable for gasoline and diesel blending. The catalyst continuously circulates through the system, being regenerated by burning off carbon deposits. FCC units are among the most active and visually dramatic parts of a refinery, operating non-stop and producing large volumes of gasoline-range material. Hydrocracking is another upgrading step used especially for heavier crude oils. In hydrocrackers, heavy hydrocarbons are mixed with hydrogen and passed over catalysts under high pressure and temperature. This process breaks molecules apart while also removing sulfur and nitrogen impurities. Hydrocracking produces very clean gasoline components along with jet fuel and diesel. The hydrogen-rich environment helps produce fuels that meet modern emission standards. Throughout these processes, sulfur removal is essential. Crude oil naturally contains sulfur, which must be reduced to extremely low levels. Hydrodesulfurization units treat gasoline components by reacting them with hydrogen over catalyst, converting sulfur compounds into hydrogen sulfide gas. This gas is then processed in sulfur recovery units to produce elemental sulfur, which is sold for industrial use. Removing sulfur protects engines, reduces air pollution, and ensures regulatory compliance. Once individual gasoline components are produced, the refinery enters one of the most precise stages: blending. Gasoline is not a single substance, but a carefully engineered mixture of hydrocarbons and additives. Blending systems combine reformate, cracked gasoline, alkylate, isomerate, and other components in exact proportions. Each blend must meet strict specifications for octane rating, vapor pressure, energy content, and emissions performance. Computer-controlled blending systems adjust ratios in real time based on laboratory feedback. Additives are also introduced during blending. These may include detergents to keep engines clean, corrosion inhibitors to protect fuel systems, antioxidants to prevent degradation, and anti-knock compounds. Seasonal adjustments are made as well. Summer gasoline is formulated differently than winter gasoline to control evaporation and emissions in varying temperatures. Each batch is tested repeatedly to ensure compliance before it leaves the refinery. Quality control is constant. Refinery laboratories operate around the clock, analyzing fuel samples using advanced instruments. Technicians measure octane ratings, density, sulfur content, vapor pressure, and distillation curves. Even slight deviations can cause performance issues or regulatory violations. If a batch fails testing, it is reblended or reprocessed. After blending and approval, gasoline moves to storage. Large tank farms store millions of gallons of finished fuel in floating roof or fixed roof tanks designed to minimize vapor loss and contamination. These tanks are monitored for temperature, pressure, and volume. From storage, gasoline enters the distribution network. Transportation is the final step in the journey. Gasoline is moved primarily through pipelines to regional terminals. Pipelines operate continuously, pushing batches of different fuels separated by interface zones that are later reprocessed. At terminals, additional additives may be injected to meet local requirements. Tanker trucks then deliver gasoline to individual gas stations, where it is stored underground until pumped into vehicles. Behind the scenes, refinery operations are tightly controlled for safety and environmental protection. Refineries contain thousands of sensors monitoring pressure, temperature, flow, and chemical composition. Automated shutdown systems activate instantly if abnormalities occur. Workers undergo extensive training, and facilities are designed with multiple containment layers to prevent spills or leaks. Environmental systems are integral to modern refineries. Wastewater treatment plants clean water before reuse or discharge. Air emissions are scrubbed and filtered. Heat recovery systems capture energy from hot process streams to improve efficiency. Many refineries operate cogeneration plants that produce both electricity and steam, reducing overall energy consumption. What makes gasoline production remarkable is the scale and precision involved. Refineries process hundreds of thousands of barrels of crude oil every day, yet the final gasoline must meet exact chemical standards to perform reliably in millions of different engines. The transformation from thick crude oil to clear, high-performance fuel requires chemistry, physics, mechanical engineering, and automation working together seamlessly. From underground oil reservoirs to towering distillation columns, from cracking reactors to blending manifolds, The journey of gasoline is one of the most sophisticated industrial processes ever developed. Every acceleration, every commute, and every long drive depends on this hidden system operating flawlessly day after day. And that is exactly how gasoline is distilled, cracked, reformed, cleaned, blended, tested, stored, and delivered from crude oil inside modern refineries. A powerful demonstration of industrial chemistry and engineering at massive scale. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, processes, and factories that power everyday life. Every day, millions of bananas are enjoyed by people all over the world, from breakfast tables to smoothie bowls. But the journey of a banana from tropical plantation to your kitchen is far more complex, fascinating, and meticulous than most of us ever realize. And in this video, we're going to dive deep into the incredible process of how billions of bananas are harvested, processed, shipped, and finally delivered to supermarkets and homes worldwide, uncovering the machinery, labor, and logistics that make this global fruit industry possible. Starting right at the very beginning with the banana plant itself, which is often mistaken for a tree but is actually an herbaceous plant that can grow anywhere from 6 to 20 feet tall, depending on the variety, climate, and soil conditions, with its large, broad leaves capturing sunlight and its sturdy pseudosteam supporting massive bunches of bananas, sometimes weighing up to 100 kilograms per stalk. And it all begins with the flowering of the banana plant, which produces a long purple-red inflorescence known as the banana flower or banana heart, from which the individual banana fingers start to form in clusters called hands, and each plant generally produces only one large bunch in its lifetime, requiring careful monitoring by farmers for proper growth, pest management, and disease prevention. Since bananas are highly susceptible to pests like the banana weevil, and diseases such as the devastating Panama disease, which has wiped out entire banana varieties in the past, making the selection of resistant cultivars and sustainable farming practices critical to the health of the plantation and the stability of the global banana supply. And once the bananas have reached the appropriate stage of maturity, usually when they are still green to ensure they can survive transport, they are carefully harvested, a process that is far from simple due to the weight of the bunches and the delicate nature of the fruit, which bruises easily and can spoil if mishandled. And on large plantations, teams of skilled workers use sharp machetes or long-handled knives to cut the bunch from the plant, sometimes with the assistance of cranes or mechanical lifts for the heaviest loads, immediately followed by washing and sorting to remove dirt, latex, and insects, as well as grading each banana by size, shape, and quality, often using advanced machinery to automate the process in high-volume operations, while smaller or artisanal farms rely on human inspection to ensure only the highest quality bananas are packaged for shipment. And after sorting, the bananas are carefully packed into ventilated, corrugated cardboard boxes designed to protect the fruit during long-distance transport, usually by refrigerated trucks or cargo ships that maintain temperatures around 13 to 14 degrees Celsius to prevent premature ripening and spoilage. And the logistics involved in this global supply chain are staggering, as bananas harvested in Ecuador may be on a journey lasting several weeks before they arrive in Europe or North America, with timing and coordination being essential to ensure the fruit reaches ripening facilities at exactly the right stage, where temperature, humidity, and ethylene gas are controlled to trigger uniform ripening, transforming the green, firm bananas into the familiar yellow, sweet, and soft fruit that consumers recognize. And these ripening rooms are marvels of modern agricultural engineering, capable of handling millions of bananas at a time, with sophisticated ventilation systems, ensuring even gas distribution and monitoring technology that tracks ripeness levels in real time, while maintaining conditions that minimize waste and prevent over-ripening. And speaking of waste, the banana industry also faces environmental and social challenges, including deforestation, water use, pesticide application, labor practices, and the threat of monoculture vulnerabilities, which has led many companies and farms to adopt sustainable certifications, fair trade practices, and more eco-friendly growing methods, from integrated pest management to organic cultivation and improved waste management, all aimed at reducing the ecological footprint of banana production while supporting the livelihoods of workers and communities in producing regions. And after the ripening process, the bananas are transported to supermarkets and retailers around the world, often via refrigerated trucks and air-conditioned containers, where they are carefully displayed to maintain freshness, with constant monitoring to rotate stock and reduce spoilage, ensuring that consumers receive bananas that are not only aesthetically perfect, but also delicious and safe to eat. And while this may seem like a simple fruit, the story of bananas is a testament to human ingenuity, precision agriculture, and global coordination, as the industry supports millions of jobs, feeds billions of people, and represents a multi-billion-dollar business that has been shaped by centuries of cultivation, trade, and technological innovation. And beyond the plantations, processing also includes producing banana-based products, such as dried bananas, banana chips, purees, baby food, and even banana-flavored snacks, each requiring specialized processing techniques, quality control measures, and packaging solutions to preserve flavor, texture, and nutritional value, all while meeting stringent food safety standards and international export regulations. And the remarkable scale of banana production is highlighted by the fact that an estimated 100 billion bananas are consumed globally every year, meaning that at any given moment, countless workers, machines, and logistical systems are at work moving bananas from tropical farms to distant shelves. And this includes the countless small details that ensure quality, from washing and waxing bananas to applying protective coatings in some cases, to monitoring ripeness using color charts and ethylene gas sensors, to coordinating shipping schedules across oceans, ports, and land transportation, all of which requires a combination of advanced technology and human expertise. And even the banana packaging itself is carefully designed to withstand rough handling during transit, often incorporating padding, airflow designs, and moisture control, while also minimizing environmental impact, with some companies experimenting with biodegradable materials and reusable crates, highlighting how even a humble banana reflects modern challenges and solutions in agriculture, sustainability, and global trade. And yet, despite the immense scale and complexity, the ultimate goal remains simple: delivering fresh, tasty, and nutritious bananas to millions of people around the world every day, a process that combines centuries of agricultural knowledge with cutting-edge technology and meticulous planning. And next time you peel a banana, it's worth remembering that this simple act connects you to a global network of farmers, scientists, engineers, and logisticians, all working together to ensure that one of the world's most beloved fruits reaches your table in perfect condition. And the story of bananas also highlights fascinating cultural, economic, and scientific aspects, from the domestication of wild banana species in Southeast Asia thousands of years ago, to the modern development of disease-resistant varieties, the expansion of plantations in Latin America, Africa, and Asia during colonial and post-colonial periods, and the ongoing research into sustainable farming practices and genetic improvements that promise to secure banana production for the future, while simultaneously addressing climate change, soil depletion, water management, and ethical labor practices, all of which make the banana industry a prime example of how global food systems are intricately interconnected and reliant on both natural ecosystems and human ingenuity. And as we explore the banana journey from farm to table, we see how labor-intensive the process is, with teams of workers coordinating planting, maintenance, harvesting, sorting, packaging, and shipping on an almost industrial scale, often facing challenging working conditions, yet demonstrating remarkable skill, precision, and resilience. And despite technological advances like automated sorting machines, cranes, and shipping containers with climate control, human oversight remains critical to ensure quality, detect defects, and manage complex logistics, proving that even in an age of mechanization, the human touch is essential in delivering billions of bananas worldwide. And this intricate combination of biology, agriculture, engineering, logistics, and economics is why the banana story is not just about fruit, but about the astonishing journey of how billions of bananas are harvested and processed every year, connecting tropical farms to urban markets, feeding communities, sustaining economies, and illustrating how something as simple as a banana reflects the incredible complexity, coordination, and care involved in modern global food production. A story that continues to evolve as new technologies, sustainability practices, and scientific innovations shape the future of banana farming, ripening, and distribution, ensuring that for generations to come, bananas remain one of the most accessible, delicious, and universally loved fruits on the planet. And this remarkable journey from the tropical sun to your table reminds us that even everyday items carry incredible stories, and understanding the full life cycle of bananas gives us a greater appreciation for the hidden systems and human effort that make our lives possible, highlighting that behind every peel lies decades of agricultural tradition, modern scientific research, international logistics, and global collaboration, all converging to deliver billions of bananas every year to people across the globe. Protein powder has become one of the most widely consumed nutrition products on Earth, used by athletes, bodybuilders, medical patients, and everyday consumers looking for convenient protein intake. Yet behind every scoop is a vast industrial process involving agriculture, chemical separation, filtration technology, massive drying towers, precision blending, laboratory testing, and high-speed packaging lines. What looks like a fine flavored powder inside a plastic tub is actually the final stage of a tightly controlled food engineering system designed to deliver consistent nutrition, safety, taste, and shelf stability at enormous scale. And today on the How Factory, we're going inside modern protein powder manufacturing facilities to see exactly how protein powder is made, from raw ingredients to the final sealed tub shipped worldwide. The journey begins with the protein source itself. For whey protein, the most common type, production starts in dairy processing plants. Raw milk arrives from farms in refrigerated tanker trucks and is immediately tested for fat content, protein levels, antibiotics, and microbial safety. After approval, the milk is pasteurized and separated into cream and skim milk. During cheese production, enzymes are added to coagulate milk proteins into curds. What remains is liquid whey. Once considered waste, now one of the most valuable raw materials in sports nutrition. This whey is mostly water, but it contains lactose, minerals, and dissolved proteins that must be concentrated and purified. For plant-based protein powders, the starting point looks very different. Ingredients such as peas, soybeans, rice, or oats arrive at processing plants in bulk. These crops are cleaned using vibrating screens, air separators, and magnets to remove dirt, stones, and metal fragments. The clean raw material is then milled into flour and mixed with water to form a slurry. Mechanical separators and centrifuges remove fiber and starch, isolating the protein-rich fraction. Whether dairy-based or plant-based, the next goal is the same: separating protein from everything else. This separation happens using advanced filtration systems. Large stainless steel membrane units perform microfiltration and ultrafiltration, forcing liquid protein through extremely fine filters. These membranes allow water, sugars, and small molecules to pass through while trapping protein molecules. Pumps continuously circulate the liquid through multiple filtration stages, gradually increasing protein concentration. For whey protein isolate, which contains very little lactose or fat, additional filtration passes are required. Sensors monitor flow rate, pressure, temperature, and protein concentration in real time. Any deviation can affect purity or efficiency, so the process is tightly controlled. Once the protein is sufficiently concentrated, it exists as a thick liquid. But protein powder must be dry, stable, and shelf-ready, which brings the process to one of the most dramatic stages: spray drying. The liquid protein is pumped into towering spray drying chambers that can reach several stories high. Inside, high-pressure nozzles atomize the liquid into millions of tiny droplets. Hot, filtered air rushes through the chamber, instantly evaporating moisture. In seconds, liquid protein becomes fine powder. Temperature control here is critical. Too hot and the protein denatures. Too cool and moisture remains. Cyclone separators collect the dried powder while removing fine particles from the airstream. The freshly dried protein powder is transferred through enclosed pipelines to storage silos. These rooms are climate-controlled to prevent moisture absorption, because protein powder is highly hygroscopic. At this stage, the powder is unflavored and nutritionally pure but not yet ready for consumers. Before moving on, samples are sent to on-site laboratories where technicians test protein percentage, moisture content, microbiological safety, and amino acid profile. Only approved batches are released for formulation. Next comes blending, the stage where protein powder becomes a finished consumer product. In large blending halls, stainless steel ribbon blenders or paddle mixers combine base protein powder with flavor systems and functional ingredients. Depending on the product, these additions may include cocoa powder, vanilla compounds, sweeteners, vitamins, minerals, enzymes, electrolytes, or thickening agents. Each ingredient is weighed with high precision, often using automated dosing systems connected to formulation software. Even small errors could affect flavor or nutritional accuracy. Blending must be thorough but gentle. Overmixing can damage fragile ingredients or alter particle size, while undermixing leads to inconsistent taste and nutrition. Mixing times, blade speeds, and batch sizes are carefully calibrated. Quality teams pull samples from multiple points inside the blender to confirm uniformity. Every scoop from the final product must contain the same protein content and flavor intensity. Flavor development plays a major role at this stage. Protein on its own can taste bitter or chalky, so food scientists design flavor systems specifically to mask off notes while maintaining stability over months of storage. Flavors must survive humidity, oxygen exposure, and temperature changes without breaking down. Sweeteners are chosen based on solubility, sweetness profile, and consumer preference. Extensive sensory testing ensures that the finished powder dissolves smoothly and tastes consistent from batch to batch. Once blended, the powder undergoes another round of quality control. Laboratories test protein concentration, moisture level, solubility, density, and flow characteristics. Microbial tests confirm the absence of harmful bacteria, yeast, or mold. Heavy metal screening ensures compliance with food safety regulations. If any parameter falls outside specification, the batch is quarantined for investigation or reprocessing. After approval, the powder moves to packaging, one of the fastest stages in the facility. Packaging areas are kept under controlled air conditions to prevent contamination. Empty plastic tubs arrive on conveyors and pass through air blast cleaning stations that remove dust and static. Automated auger fillers or weight-based dosing machines dispense exact amounts of powder into each container at high speed. These machines can fill dozens of tubs per minute with accuracy measured in grams. Before sealing, many tubs receive desiccant packets to absorb moisture and extend shelf life. Foil induction sealers heat bond protective liners to the tub rim, creating an airtight barrier. Lids are then applied and torqued to specification. Tamper-evident bands or seals ensure product integrity for consumers. Each filled container passes over a check weigher that confirms correct fill weight. Any underfilled or overfilled tub is automatically rejected. Labeling follows immediately. High-speed labelers apply branded labels that include nutrition facts, ingredient lists, allergen warnings, batch numbers, and expiration dates. Vision systems inspect label placement and print clarity. Inkjet or laser coders mark each tub with traceability codes, allowing manufacturers to track every unit back to its production run. Next comes secondary packaging. Automated case packers group tubs into cardboard boxes which are sealed and labeled for shipping. Robotic palletizers stack boxes into stable pallets optimized for transport efficiency. Pallets are stretch-wrapped and logged into warehouse systems that track inventory in real time. From here, products move to distribution centers, retailers, gyms, hospitals, or direct-to-consumer fulfillment hubs. Behind the scenes, sanitation and hygiene never stop. Protein powder facilities operate under strict food manufacturing standards, similar to pharmaceutical plants. Equipment is cleaned using clean-in-place systems that flush pipes, blenders, and dryers with hot water and sanitizing solutions. Air filtration systems maintain clean environments in blending and packaging zones. Employees wear protective clothing and follow strict handling procedures to prevent contamination. Sustainability is increasingly important in modern protein manufacturing. Many facilities recycle water used in filtration processes. Energy-efficient spray dryers reduce fuel consumption. Waste heat is captured and reused. Packaging is redesigned to reduce plastic use or improve recyclability. Plant-based proteins continue to grow in popularity as manufacturers seek lower environmental impact and diversified sourcing. What makes protein powder manufacturing remarkable is how it transforms raw agricultural materials into precise nutritional products. Whether derived from milk or plants, protein must be isolated, purified, dried, blended, tested, and protected with extreme care. The final product must deliver exact nutrition, dissolve smoothly, taste consistent, and remain stable for months, all while being produced at massive scale. From liquid whey or milled crops to fine powder sealed inside a tub, the journey involves kilometers of stainless steel piping, advanced filtration membranes, towering spray dryers, laboratory testing, and robotic packaging lines. Every scoop represents hours of processing and countless quality checks hidden behind a simple container. And that is exactly how protein powder is filtered, dried, blended, flavored, tested, sealed, and packaged. A sophisticated fusion of food science, chemical engineering, and industrial automation, powering one of the world's most popular nutritional products. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, systems, and factories behind everyday products. Every 30 seconds, somewhere on Earth, a brand new Tesla rolls off the assembly line. It's fast, precise, and largely run by machines that never sleep. But how can a single factory produce thousands of high-tech electric cars every day with such surgical precision? Today on The How Factory, we're diving inside Tesla's gigafactories to see how innovation, automation, and engineering come together to build a car every half minute. The journey starts long before any metal is bent or battery is charged. It starts with design and data. Tesla's vehicles are engineered entirely in 3D digital models that link directly to robots on the factory floor. Every bolt, panel, and weld is planned by software so the machines already know what to do before materials arrive. In the Gigafactory, there's no blueprint on paper, just millions of lines of code. Next comes the raw material. Trucks and trains deliver giant rolls of aluminum and steel to the press shop. These rolls feed into massive stamping presses that hit with thousands of tons of force. Each impact shapes a door, roof, or hood panel in less than a second. The noise is deafening, a heartbeat of industrial power. Robots transfer the freshly pressed parts to stacking lines for inspection. Cameras check for even the slightest wrinkle or dent. If the computer finds a flaw, the panel is recycled immediately. Once the body panels are ready, they move to the body shop, the heart of Tesla's automation empire. Rows of orange robot arms from KUKA and Fanuc spark and move in perfect rhythm. Here, humans are few, robots are many. Each arm can weld faster and more precisely than any human ever could. More than 5,000 spot welds hold each car together, and the robots complete them in minutes. Laser measuring systems confirm every joint is within fractions of a millimeter. Any error means instant shutdown for that station until the line is perfect again. Tesla calls this phase the machine that builds the machine, because every arm, sensor, and conveyor works as part of a bigger mechanical organism. The robots move with choreographed grace, like industrial ballet, passing the car body from one to another as if they were dancers in a metal performance. At any moment, hundreds of car frames are moving through different stages simultaneously. That's how Tesla maintains its rhythm. A new car frame emerges roughly every half minute. Next comes the paint shop. This is where raw metal turns into a work of art. Each bare shell enters an enclosed chamber for a chemical bath that cleans and protects the metal. Then, automated robots spray layers of primer, base color, and clear coat in climate-controlled rooms. Temperature, humidity, and airflow are monitored second by second. Tiny particle filters ensure no dust ruins the mirror finish. Depending on the color, a Tesla body spends 6 to 10 hours in painting and baking ovens before it gleams like liquid glass. Paint shops are the cleanest areas in the factory, más veces the squin. Workers wear anti-static suits and air is recycled through giant filters. After painting, the body moves to the general assembly area. This is where technology meets craftsmanship. Robots still assist, but humans take over for precision tasks. Workers install the wiring harness, the nervous system of the car, carefully threading hundreds of meters of cable through tunnels and panels. Every plug snaps into place with a distinct click. Touchscreens, sensors, and cameras are connected next. Quality inspectors double-check each connection because one loose wire could disable a feature like autopilot. Then come the interiors. Seats, dashboards, and carpets arrive on their own subassembly lines and slide into the main chassis with robotic precision. Tesla designs most components in-house, so each piece fits perfectly without extra adjustment. Modular construction means a Model Y and a Model 3 share many parts, cutting build time and costs. Even the screws are tracked by software to ensure none are missed. If one fails a torque test, the car is flagged for review immediately. Beneath the floor, the heart of every Tesla awaits, the battery pack. Gigafactories don't just assemble cars, they build batteries too. In vast clean rooms, thousands of battery cells are arranged into modules and then into packs. Robots apply coolant, insulation, and seals with microscopic accuracy. Each battery pack is tested for voltage and thermal stability before it ever touches a car. Once approved, robot cranes lift the entire pack into the vehicle chassis from below, a single operation that takes less than 2 minutes. Now the car is coming alive. Suspension and drive units are bolted on. Electric motors slide into place with robotic arms. The undercarriage is sealed and cables are connected to the battery and motor controllers. Software technicians begin programming the vehicle even before it leaves the line. Each Tesla gets its own digital profile, VIN number, and firmware installed automatically. That's when the screen lights up for the first time, the car's first heartbeat. Next comes testing. Every vehicle undergoes hundreds of automated checks. Cameras scan panel gaps and paint surfaces for imperfections. Ultrasonic sensors listen for air leaks. Machines simulate braking and steering before the wheels even touch pavement. If any system fails, the car is pulled for manual inspection. Only after passing everything does it reach the roll test, where each Tesla drives on a rolling dyno to check motor performance and noise. In the final stage, water jets blast the car to verify weather seals and wipers. No vehicle leaves without perfection. Outside the final checkpoint, rows of fresh cars shine under sunlight. Each was built in less time than a coffee break. Forklifts move them to charging bays where software updates are loaded over Wi-Fi. Technicians perform a last digital inspection before shipping. From here, cars travel by train or truck to delivery centers around the world. By the time a customer takes delivery, the entire journey, from raw metal to drivable EV, has taken just a few days. As the finished cars charge and wait for shipment, Tesla's network of gigafactories keeps humming day and night. Every process is timed, measured, and analyzed by thousands of sensors. Data flows constantly from the factory floor to Tesla's central servers, where algorithms track efficiency, energy use, and even how individual robots behave. Nothing inside a gigafactory happens by chance. It's a living ecosystem of machines guided by artificial intelligence and real-time feedback. Inside the control rooms, massive dashboards glow with live statistics. Number of cars built, energy consumed, parts used, and defects detected. Engineers can pinpoint a single bolt on a specific vehicle anywhere on the line. If a robot's movement slows by even a fraction of a second, the system flags it instantly. This is what Elon Musk means when he calls the Gigafactory the machine that builds the machine. It's not just about cars, it's about a self-improving organism that learns as it produces. To sustain that rhythm, Tesla relies on scale and vertical integration. Traditional car makers buy most components from suppliers. Tesla manufactures many of its own: batteries, seats, electronics, even charging ports. By keeping production in-house, the company reduces shipping delays and quality issues. Each factory functions like a small city. Raw materials arrive at one end, and finished cars drive out the other. In Shanghai, Berlin, and Austin, that flow happens almost without interruption, with deliveries leaving 24 hours a day. Automation doesn't mean humans disappear. Skilled technicians, software engineers, and quality specialists still fill every corner of the plant. People handle the tasks that require sensitivity and judgment, aligning trim, verifying welds, troubleshooting errors. They're backed by robots that handle the repetitive, dangerous, or ultra-precise jobs. Together, they form a hybrid workforce that blends human intelligence with machine consistency. Tesla's goal isn't full automation, it's perfect collaboration. Energy efficiency drives every decision. Gigafactories are powered largely by renewable sources: solar arrays on rooftops, wind contracts, and battery storage built from Tesla's own power packs. Waste heat from furnaces is captured to warm other sections of the plant. Excess electricity charges internal fleets of electric forklifts and logistics vehicles. Even the air handling systems recycle filtered air to minimize loss. The idea is to create a closed-loop factory where nothing is wasted, not even the energy that powers production. Scrap metal and rejected panels don't go to landfills. They're melted down and re-rolled within the same facility, ready for another round of stamping. Paint overspray is captured and filtered. Water from cleaning tunnels is purified and reused. In Tesla's ecosystem, every process feeds another. The factory becomes a loop of material, motion, and power that never truly stops. In the battery lines, the scale is even more astonishing. Thousands of small cylindrical cells zip along conveyors at blinding speed. Machines weld, glue, and test them with almost zero human touch. The tolerances are microscopic. Fractions of a millimeter separate success from failure. Finished modules feed into robotic arms that assemble full packs destined for cars or energy storage systems. A single gigafactory can produce enough cells for hundreds of thousands of vehicles each year. Each completed car is more than a machine of metal and wires. It's also a computer on wheels. Before shipping, technicians load the latest firmware, calibrate cameras, and activate sensors. The vehicle wakes up for the first time. Screens glow, motors hum softly, and software begins its self-tests. Tesla's operating system is what sets it apart. Unlike traditional automakers who freeze software at the factory, Tesla treats cars like smartphones. Over-the-air updates keep improving performance, safety, and features long after purchase. In the testing zone, engineers drive finished cars through short obstacle courses to verify handling and braking. Others run virtual diagnostics, checking every subsystem remotely. The process is ruthless. Even minor issues trigger re-inspection. When a car passes, it's wrapped for shipping, its battery charged to about 50% for optimal transport, and its destination tag affixed. Trucks and trains haul thousands each week to ports and distribution centers worldwide. In some regions, cars are loaded directly onto electric haulers powered by the same technology they carry. Step back for a moment and imagine the full scale. Thousands of parts, hundreds of robots, and miles of conveyor belts, all synchronized so precisely that a new Tesla body rolls out every 30 seconds. The coordination is staggering. At peak output, a single gigafactory can produce nearly 1 million vehicles a year. To keep that momentum, software constantly adjusts pacing, ordering parts just in time, and rerouting flow when sensors detect bottlenecks. It's the manufacturing equivalent of a living nervous system. Training this system took years of trial and error. Early Tesla factories were chaotic. Robots collided, sensors misread signals, and production halted unexpectedly. Musk famously slept on the factory floor during the Model 3 ramp-up to find and fix problems firsthand. Out of those painful lessons came better design, modular stations, smarter sensors, and standardized parts. The result is today's rhythm: fast, repeatable, and scalable worldwide. Each new gigafactory learns from the last. Berlin adopted cleaner paint systems and faster stamping presses. Texas introduced the Giga Press, one of the largest casting machines on Earth, which can mold huge sections of a car's frame in a single shot. That innovation replaced dozens of welded parts, cutting weight and complexity. Watching molten aluminum pour into a gigapress mold is like witnessing modern alchemy. Liquid metal transforming into structure in seconds. The gigapress symbolizes Tesla's obsession with simplification. Fewer parts mean fewer robots, less assembly time, and greater strength. Combined with new 4,680 battery cells, which double energy density, these changes will define Tesla's next generation. Each improvement ripples through the entire ecosystem, making cars cheaper to build, lighter to drive, and faster to produce. Beyond efficiency, the factories are expanding into new frontiers. Future lines will assemble Cybertrucks and semi-trucks, vehicles demanding entirely new techniques for stainless steel exoskeletons and heavy-duty components. Tesla's engineers are already building specialized presses and robots to handle them. The same AI systems that once optimized sedan production are being retrained to manage these new designs. Adaptability is the ultimate advantage. Inside every gigafactory, there's also a quiet revolution in data. Machine learning models predict wear on equipment, analyze supply chain risks, and even forecast weather patterns that could affect deliveries. By anticipating problems before they occur, Tesla keeps the line running while competitors scramble to react. It's predictive manufacturing on a scale the automotive world has never seen. The pace of production isn't just about speed, it's about philosophy. Traditional car companies separate design, production, and software into silos. Tesla merges them into one continuous feedback loop. When a design tweak improves assembly time by half a second, it's implemented instantly. Updates flow from digital models to robots within hours, not months. The result? A company that iterates as fast as its code can compile. And the effect shows. Each Tesla that leaves the line represents the future of manufacturing, efficient, connected, and constantly evolving. From raw aluminum to a self-driving electric car in just a few days, Tesla's factories redefine what's possible. They're not just building vehicles, they're rewriting the playbook for global industry. Walk through the final delivery lot, and you'll see rows of gleaming cars lined up like a metallic army. Each one charged, tested, and waiting for transport. In a few days, they'll be on highways across the world, silently accelerating toward the future. Every 30 seconds, another joins them, built by the most advanced production system on the planet. So the next time you see a Tesla glide past, remember the choreography behind it. The molten metal, the roaring presses, the tireless robots, and the people guiding them all. Every detail, every spark, every second contributes to that one incredible statistic: a brand new car every half minute. That's not just manufacturing, that's the rhythm of innovation. And that's how Tesla builds a car every 30 seconds. Thanks for watching The How Factory, where we uncover how the world really works. Don't forget to like, subscribe, and stay tuned for more stories from the heart of human ingenuity. Oreo cookies may look like a simple combination of 2 chocolate wafers and a white cream filling. But behind every perfectly aligned cookie is one of the most advanced, high-speed food manufacturing systems in the world. Produced by the billions each year, Oreos rely on massive automated production lines that blend raw agricultural ingredients, precision baking technology, robotic handling, vision inspection, and non-stop packaging systems capable of operating around the clock. What appears to be a humble snack is actually the result of extreme consistency engineering, food science, and industrial-scale efficiency designed to ensure every Oreo tastes, looks, and feels exactly the same no matter where it's made. And today on The How Factory, we're going deep inside mega cookie factories to see exactly how Oreo cookies are manufactured from raw ingredients to sealed packages ready for global distribution. The journey begins with raw ingredients arriving at the factory in bulk quantities. Flour, sugar, cocoa powder, vegetable oils, leavening agents, salt, and flavorings are delivered by tanker trucks, rail cars, or palletized shipments. These ingredients are stored in massive silos or climate-controlled storage rooms designed to protect them from moisture, pests, and contamination. Before entering production, every ingredient is tested for quality, particle size, moisture content, and consistency. Even small variations can affect dough behavior, baking performance, or final texture, so strict quality control begins before mixing ever starts. Dough production is the first major manufacturing stage. Industrial mixers, some large enough to process thousands of kilograms per batch, combine flour, cocoa powder, sugar, fats, and liquid ingredients into a dense, dark dough. These mixers use carefully programmed speeds and mixing times to develop the correct structure without overheating the dough. Temperature control is critical because excessive heat can alter fat behavior and weaken texture. Sensors continuously monitor dough consistency, viscosity, and temperature, adjusting mixing parameters automatically. Once mixed, the dough rests briefly to allow hydration and uniformity before shaping. From the mixers, the dough moves onto forming lines. High-pressure extrusion systems push the dough through shaping dies that form the iconic Oreo wafer discs. Rotary molding machines press the dough into patterned molds that imprint the familiar Oreo design, logos, and decorative edges. Excess dough is trimmed away and recycled back into the system, minimizing waste. The formed wafers are transferred onto long conveyor belts that feed directly into industrial baking ovens. Baking is one of the most critical steps in Oreo production. The ovens used are continuous tunnel ovens that can stretch hundreds of feet long. As the wafer discs travel through the oven, they pass through carefully controlled temperature zones. Initial zones set the shape and expand the dough slightly, while later zones drive off moisture and develop the wafer's crisp texture. Baking times are measured in minutes, but precision is everything. Underbaked wafers remain soft, while overbaked wafers become brittle and bitter. Computer systems monitor oven temperatures, airflow, humidity, and belt speed in real time to maintain perfect consistency. As the wafers exit the oven, they are fully baked but extremely fragile. Cooling tunnels immediately reduce their temperature to stabilize structure and prevent breakage. Cooling must happen gradually. Rapid temperature changes can cause cracking or warping. Fans and airflow systems gently bring the wafers down to room temperature while maintaining alignment on the conveyor. While wafers are baking and cooling, the cream filling is produced in parallel. The filling is made from a blend of sugar, vegetable fats, flavorings, and emulsifiers. Large mixing tanks whip these ingredients together under controlled conditions to produce a smooth, stable cream with a specific density and texture. The cream must be soft enough to spread easily but firm enough to hold its shape once sandwiched between wafers. Temperature control is critical here as well. Fats must remain within a narrow range to avoid separation or graininess. Once wafers and cream are ready, the process moves to one of the most impressive stages: sandwiching. High-speed assembly machines align two wafers with extreme precision. A measured dollop of cream is deposited onto the center of one wafer using synchronized nozzles. The second wafer is placed on top and gently pressed down to spread the cream evenly. These machines operate at astonishing speeds, assembling thousands of Oreo cookies every minute. Vision systems verify alignment, cream placement, and wafer integrity in real time. Any cookie with misaligned wafers, cracked surfaces, or missing filling is automatically removed from the line. After sandwiching, the cookies move through stabilization conveyors that allow the cream to settle and firm slightly. This ensures the cookies maintain their structure during packaging and transport. At this stage, additional inspections occur. Cameras check thickness, diameter, and color consistency. Weight sensors verify that each cookie meets specification. Consistency is paramount. Consumers expect every Oreo to look and taste identical. Next comes packaging, another highly automated operation. Finished cookies are guided into precise stacks using robotic arms or synchronized conveyor systems. These stacks are then wrapped in protective inner packaging that maintains freshness and prevents breakage. Plastic films or foil laminates are heat-sealed around the stacks, creating airtight packs. Packaging machines operate continuously, matching the speed of the baking line so production never slows. Wrapped stacks move to secondary packaging, where they are loaded into branded boxes, trays, or multi-packs depending on the product format. Robotic packers place wrapped cookies into cartons with millimeter-level precision. Each package is weighed and scanned to ensure correct count and integrity. Barcodes, expiration dates, and batch codes are printed for traceability. Any package that falls outside specification is rejected automatically. Behind the scenes, quality assurance teams monitor the entire operation. Samples are pulled regularly for texture testing, moisture analysis, flavor evaluation, and shelf life stability. Oreos must maintain their crunch, cream texture, and flavor balance for months under various storage conditions. Accelerated aging tests simulate temperature and humidity extremes to ensure performance throughout the product's lifespan. Food safety is another constant priority. Oreo factories operate under strict sanitation protocols. Equipment is cleaned regularly using clean-in-place systems that flush mixers, pipes, and nozzles with hot water and sanitizing agents. Air filtration systems maintain clean production environments. Workers follow hygiene protocols, including protective clothing and controlled access zones. Allergen management systems prevent cross-contamination between product lines. The scale of Oreo manufacturing is staggering. A single mega factory can produce millions of cookies per day, operating multiple parallel lines simultaneously. Raw ingredients flow continuously into mixers, while finished products exit the other end ready for distribution. Downtime is minimized through predictive maintenance, where sensors monitor machinery wear and alert technicians before failures occur. Every second of operation is optimized for efficiency. Once packaged, Oreo products move into automated warehouses. Conveyor systems transport pallets to storage areas where inventory is tracked digitally. From there, products are shipped to distribution centers, retailers, and international markets. Logistics planning ensures cookies reach store shelves quickly while maintaining freshness. Oreos produced in one country may be consumed halfway around the world within weeks. Sustainability also plays an increasing role in modern cookie production. Manufacturers work to reduce energy consumption in ovens, recycle waste dough, and minimize packaging materials. Water used in cleaning processes is filtered and reused where possible. Continuous improvements aim to reduce environmental impact while maintaining production scale. What makes Oreo manufacturing remarkable is not just the speed, but the precision. Baking, filling, and assembly must occur within extremely tight tolerances to maintain the brand's signature experience. The texture of the wafer, the sweetness of the cream, the alignment of the sandwich, all are engineered and monitored continuously. The iconic twist, lick, dunk experience depends entirely on industrial consistency achieved at massive scale. From raw flour and cocoa powder to perfectly stacked cookies sealed inside familiar blue packages, the Oreo production process is a seamless blend of food science, mechanical engineering, automation, and logistics. Every cookie represents a balance between softness and crunch, sweetness and bitterness, tradition and technology. And that is exactly how Oreo cookies are mixed, molded, baked, cooled, filled, assembled, inspected, packaged, and shipped on mega production lines. A hidden world of industrial precision behind one of the most recognizable snacks ever created. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, systems, and factories behind everyday products. Every day, over 2 billion servings of Coca-Cola are consumed around the world, from the bustling streets of New York to small villages in Africa. But few people have ever seen how this iconic drink is actually made. Behind every bottle is an enormous web of precision engineering, chemistry, and global logistics that has turned a 19th century soda into one of the most successful products in human history. Welcome to the How Factory, where today we take you inside the Coca-Cola factory to uncover the hidden process of how billions of bottles are produced, filled, sealed, and shipped with near-perfect consistency. What begins as simple ingredients, water, sugar, and flavoring, transforms into one of the most recognizable beverages on Earth through one of the most tightly controlled manufacturing systems ever built. It all starts with the recipe, one of the most closely guarded trade secrets in the world. Known as Merchandise 7X, the Coca-Cola formula is locked in a vault in Atlanta, Georgia. Only a few executives know the full details, but we do know its core components. A base syrup made of sugar, caramel color, phosphoric acid, caffeine, and a proprietary blend of natural flavors that give Coke its unmistakable taste. This syrup is produced in concentrated form at Coca-Cola's syrup plants, which ship it to bottling facilities worldwide. These bottlers, like often independent partners operating under strict Coca-Cola licensing, mix the syrup with purified water and carbon dioxide gas to create the finished drink. But before even a single drop of syrup touches a bottle, something far more important happens. The water is purified. Water makes up nearly 90% of a bottle of Coke, and Coca-Cola's factories treat it like liquid gold. Raw water from municipal supplies is piped into the plant and sent through a multi-stage purification system. First, sand and carbon filters remove dirt, chlorine, and organic particles. Then, reverse osmosis membranes strip away any remaining minerals or microbes. Finally, ultraviolet light and fine filtration ensure that the water meets Coca-Cola's exact purity standards. So pure, in fact, that it's often cleaner than bottled drinking water. Each plant has its own on-site water lab, where technicians continuously test pH, temperature, and chemical composition. Only after passing dozens of checks does the water flow into massive stainless steel mixing tanks, where the transformation begins. The concentrated syrup arrives in sealed barrels and is pumped into precision mixing systems that measure ingredients down to the milliliter. Depending on the country, sugar or high fructose corn syrup is added and blended until perfectly uniform. The mixture is then chilled to just above freezing, and carbonation begins. The defining step that gives Coca-Cola its fizz. Carbon dioxide gas is injected under high pressure, dissolving into the liquid to form countless microscopic bubbles. The balance between gas and syrup is meticulously calibrated. Too little and the soda goes flat. Too much and it could explode when opened. The process is fully automated, monitored by sensors that adjust in real time to maintain perfect taste and texture. Within seconds, the freshly carbonated Coca-Cola is ready to be bottled. But bottling is an engineering marvel all on its own. Each modern Coca-Cola factory contains high-speed bottling lines that can fill and cap up to 2,000 bottles per minute. That's over 100,000 per hour. The empty bottles, whether glass or PET plastic, arrive at the factory preformed or in small preforms that are expanded on-site using heat and air pressure. Before filling, they pass through a washing tunnel where jets of hot water and sterilizing agents clean every surface. In some plants, recycled bottles are used. These go through a more rigorous cleaning and inspection process involving ultraviolet light and vision systems that detect even microscopic scratches or residue. Once sanitized, the bottles move along stainless steel conveyors toward the filling machines. Massive rotating carousels fitted with dozens of nozzles. The filling system operates under high pressure to prevent the soda from losing carbonation. Each nozzle injects a precise amount of Coca-Cola into the bottle in a fraction of a second, immediately followed by a capping head that twists on the cap and seals it airtight. The entire process is synchronized with millisecond timing. Bottles move so fast they blur before the camera lens. Every few hundred bottles, sensors check weight, fill level, and seal integrity. Any outlier is automatically ejected from the line. From there, the bottles travel through labelers that apply the iconic red and white Coca-Cola branding using heat-sensitive adhesive or sleeve wrapping. The accuracy is stunning. Even at top speed, each label is placed within a 1 millimeter margin. Once labeled, the bottles move to date stamping and packaging. A laser etches batch codes and expiration dates on the neck or cap, ensuring traceability. The finished bottles are then grouped by robotic arms into trays or shrink-wrapped packs. Palletizing robots stack dozens of cases onto wooden pallets, wrapping them tightly for stability. Forklifts or automated guided vehicles, AGVs, then transport the pallets to massive climate-controlled warehouses where thousands of Coca-Cola products await shipment. In some of the world's largest plants, automated cranes and conveyor systems handle inventory with no human intervention, tracking every bottle by barcode and sending it to trucks bound for supermarkets, restaurants, and vending machines. While all of this might sound mechanical, quality control is deeply human. Throughout the factory, technicians constantly pull random samples from the production line. These are taken to on-site labs where scientists test everything: sugar content, carbonation levels, color, pH, and even the sound the bottle makes when opened. Taste testers conduct daily flavor checks to ensure that Coca-Cola in Tokyo tastes exactly like Coca-Cola in Texas. It's a level of consistency few industries can match. Behind the scenes, sophisticated software tracks every variable, from syrup ratio to bottle pressure, allowing real-time adjustments and global data analysis. Beyond the bottling line, Coca-Cola factories also focus on sustainability. Modern plants are designed to recycle up to 100% of their process water and reuse heat energy from machinery. Plastic bottles are lightweighted to use less material, and new initiatives aim to make every Coca-Cola package recyclable by 2030. Some facilities even run partially on renewable energy, solar panels and biogas from waste treatment systems. It's all part of Coca-Cola's World Without Waste strategy, an ambitious plan to reduce its environmental footprint while maintaining efficiency. Every step of this process, from syrup mixing to palletizing, is built around speed, hygiene, and precision. The machinery is so advanced that a single line can produce more than 1 million bottles per day with fewer than a dozen operators. Workers wear protective gear, and the entire bottling area is pressurized and filtered to keep out dust or insects. Each machine undergoes daily cleaning cycles with sterilizing steam and chemical rinses, ensuring zero contamination. Even downtime is calculated. Maintenance schedules are coordinated using predictive AI systems that anticipate wear and tear before a breakdown occurs. Globally, Coca-Cola operates hundreds of such bottling plants, each tailored to regional tastes and logistics. Some produce cans instead of bottles, using aluminum that's recycled continuously in closed loops. Others focus on glass for local reuse programs. Despite regional variations, the core process remains identical: a symphony of water purification, syrup blending, carbonation, filling, labeling, and packaging. The result is the same everywhere: that familiar hiss and fizz when you crack open a bottle. Economically, Coca-Cola's production model is a marvel of decentralization. Instead of one giant factory, the company licenses production to local bottlers in over 200 countries, allowing it to minimize shipping costs and adapt to local markets. A Coke bottled in Kenya might contain sugar from regional cane farms, while one in the US uses corn syrup, yet they both taste nearly identical, thanks to rigorous quality standards and chemical precision. It's this combination of local flexibility and global consistency that keeps Coca-Cola at the top of the beverage industry year after year. Behind the product's simplicity lies an astonishing scale. Every second, roughly 10,000 Coca-Cola products are opened somewhere in the world. To meet that demand, factories run 24 hours a day, 7 days a week, with multiple production lines operating in tandem. Engineers monitor systems remotely through control rooms filled with screens showing flow rates, temperatures, and pressure readings. Even the carbonation levels are adjusted automatically based on altitude, so a bottle made in Mexico City tastes the same as one made at sea level in Miami. When a pallet finally leaves the factory, it represents not just a drink, but a global operation built on science, logistics, and human coordination. From the syrup vats to the robotic arms, every piece of equipment serves a single purpose: to deliver the exact same experience to every customer, every time. And behind that perfect bottle lies more than a century of innovation, refinement, and engineering mastery. So, the next time you take a sip of an ice-cold Coke, remember what it took to make that moment possible. Millions of moving parts working in harmony to create something deceptively simple. It's not just a drink. It's a triumph of industrial design and global collaboration. That's how Coca-Cola is made inside the factory. A precise, efficient, and fascinating process that turns sugar, water, and bubbles into the world's most famous beverage. Thanks for watching The How Factory, where we explore how the world really works. Don't forget to like, subscribe, and join us for more stories about the machines, industries, and people shaping our modern world. Golf balls may look like small, simple white spheres, but they are among the most precisely engineered pieces of sports equipment ever mass-produced. Behind every perfectly dimpled ball lies a complex manufacturing process involving polymer chemistry, high-pressure molding, micron-level machining, aerodynamic testing, automated painting systems, laser inspection, and extreme quality control. What seems like a lightweight object designed to be hit across a field is actually a carefully tuned aerodynamic device built to perform consistently under tremendous impact forces and varying environmental conditions. And today, on the How Factory, we're going deep inside modern golf ball factories to see exactly how golf balls are made. From raw rubber compounds to perfectly dimpled, tour-ready spheres shipped around the world. The process begins with the core, the heart of the golf ball, which determines compression, energy transfer, and distance. Core production starts with synthetic rubber compounds delivered to the factory in pellet or slab form. These compounds are proprietary blends of polybutadiene rubber, zinc oxide, fillers, and chemical initiators. Each ingredient is weighed with extreme precision before entering industrial mixers. Inside large internal mixers, rotating blades knead the rubber under heat and pressure, ensuring the chemicals disperse evenly. This mixing stage is critical because even slight inconsistencies can alter compression and rebound performance. Once mixed, the rubber compound is rolled into sheets and cut into small pellets, each measured to create identical cores. These pellets are fed into high-pressure molding presses where the core is formed. Inside steel molds, heat and pressure trigger chemical cross-linking that transforms soft rubber into a solid, elastic sphere. The curing process is tightly controlled. Temperature, pressure, and time must be exact to achieve the desired hardness and resilience. After curing, the cores are ejected and cooled slowly to stabilize their structure. At this stage, they may appear dull and slightly oversized, but their internal properties are now set. Each batch of cores is weighed and compression tested. Any core outside specification is rejected and recycled back into raw material. Once the core is complete, attention shifts to building the ball's layers. Modern golf balls rarely consist of just a core and cover. Many feature multi-layer designs that control spin, feel, and trajectory. The next layer, often called the mantle, is molded over the core. Mantle materials are typically ionomer or thermoplastic compounds engineered to fine-tune energy transfer between the core and outer cover. Cores are placed into injection molding machines, where molten mantle material flows evenly around them. These machines rotate and clamp shut, ensuring the core remains perfectly centered. If a core is even slightly off-center, the ball will fly unpredictably. After mantle molding, the balls are cooled and inspected again. X-ray systems are often used at this stage to verify core centering and layer thickness without cutting the ball open. Any ball with asymmetry is automatically removed. Precision here is everything. Symmetry determines flight stability and accuracy. Next comes the most iconic feature of the golf ball, the cover and its dimples. The outer cover material plays a major role in durability, spin control, and feel. Depending on the model, covers may be made from ionomer for durability or urethane for softer feel and higher spin control favored by professional players. Cover materials arrive as pellets and are melted inside injection molding machines. Each ball half shell is molded with exact dimple patterns machined directly into steel molds. These dimples are not decorative. They are aerodynamic features designed to reduce drag and increase lift. The size, depth, shape, and arrangement of dimples are the result of extensive wind-tunnel testing and computer simulation. To apply the cover, the mantle-coated core is placed between two heated mold halves. Molten cover material is injected and pressed around the ball, filling every dimple cavity. Pressure and temperature must be precisely balanced to avoid air pockets or uneven thickness. Once the cover sets, the mold opens and the ball is released. At this point, a thin seam line may be visible where the mold halves met. This seam is carefully removed in subsequent finishing steps. After molding, balls enter a grinding and buffing stage. Automated machines gently polish the surface to remove excess material and smooth the seam without damaging the dimples. Sensors monitor pressure and rotation to ensure consistency across thousands of balls per hour. After polishing, the balls are washed and dried, preparing them for painting. Painting is a surprisingly complex operation. Golf balls must be bright white, uniform, and durable enough to withstand repeated high-speed impacts. Balls enter painting lines where robotic sprayers apply multiple thin coats of paint. Each layer must be even, too thick, and dimples lose definition. Too thin, and durability suffers. Between coats, balls pass through curing ovens where heat hardens the paint. Many factories apply a clear protective top coat that adds gloss and abrasion resistance. Once painted, the balls move to marking and branding. Logos, alignment lines, numbers, and model names are applied using pad printing machines capable of micron-level precision. The iconic numbering system helps players identify their ball, but it must also remain legible after repeated impacts. Printing inks are formulated to bond permanently to the painted surface. After printing, another curing stage ensures markings are fully set. Quality control intensifies at this stage. Vision inspection systems scan every ball, checking paint uniformity, logo placement, dimple clarity, and surface defects. Even tiny blemishes can cause aerodynamic inconsistencies. Balls that fail visual inspection are diverted automatically. Approved balls move on to physical testing. Performance testing is one of the most critical parts of golf ball manufacturing. Random samples from each batch undergo compression testing, measuring how much the ball deforms under load. Others are struck by robotic hitting machines that simulate real golf swings at controlled speeds. High-speed cameras track launch angle, spin rate, ball speed, and flight consistency. Some balls are tested in wind tunnels to confirm aerodynamic behavior. These tests ensure that balls meet the manufacturer's exact performance targets and comply with governing body regulations. Durability testing follows. Balls are fired repeatedly against steel plates or hit thousands of times by mechanical strikers to simulate extended play. The cover must resist cracking, peeling, and excessive scuffing. Paint adhesion and logo durability are also evaluated. Any failure triggers adjustments in materials or process parameters. After passing all tests, balls move to final cleaning and sorting. Automated systems group balls by model and quality grade. Even within specifications, some balls may be classified for practice use rather than premium retail packaging. This grading ensures consistent performance within each product line. Packaging is the final step. Golf balls are counted automatically and placed into sleeves, typically 3 balls per sleeve, before being inserted into branded boxes. High-speed packaging machines fold cartons, insert sleeves, and seal boxes with precision. Barcodes, batch codes, and regulatory markings are printed for traceability. Finished boxes are grouped into cases and stacked onto pallets by robotic palletizers. Behind the scenes, logistics systems manage global distribution. Golf balls are shipped to retailers, golf courses, tournament organizers, and warehouses worldwide. Inventory systems track production batches, destinations, and shelf life. Because golfers expect identical performance no matter where they buy their balls, consistency across factories and regions is critical. Sustainability also plays a growing role in golf ball manufacturing. Scrap rubber and polymer material from molding is collected and recycled where possible. Energy-efficient presses and curing ovens reduce power consumption. Some manufacturers are exploring bio-based polymers and improved recycling methods for used balls recovered from courses. What makes golf ball manufacturing remarkable is the combination of violence and precision. A golf ball may experience impact forces exceeding several thousand pounds in a fraction of a second, yet its structure must remain perfectly balanced. Its dimples must interact with air at high speed to produce predictable lift and drag. Its layers must work together to deliver distance, control, and feel, all within strict dimensional and weight limits. From raw rubber compounds and molten polymers to aerodynamic dimples measured in fractions of a millimeter, every golf ball is a carefully engineered system. The consistency achieved at industrial scale is what allows professionals and amateurs alike to trust the performance of each shot. And that is exactly how golf balls are mixed, molded, layered, dimpled, painted, tested, packaged, and shipped. A fusion of material science, aerodynamics, automation, and quality control hidden inside one of the smallest but most sophisticated objects in modern sports, Thanks for watching the How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, systems, and factories behind everyday products. Condoms are one of the most important public health products ever manufactured. Thin, flexible barriers designed to prevent pregnancy and reduce the transmission of sexually transmitted infections. Yet, behind every rolled latex sheath is a highly technical industrial process involving chemistry, precision dipping, curing ovens, automated testing, electronic inspection, and ultra-clean packaging environments. What appears to be a simple disposable item is actually produced under some of the strictest quality and safety standards in the consumer goods industry. And today on the How Factory, we're going inside modern condom manufacturing plants to see exactly how condoms are made, from liquid latex to finished protection trusted by millions of people worldwide. The process begins with the raw material, natural latex. Latex is harvested from rubber trees, primarily grown in tropical regions. Farmers tap the bark of mature trees, allowing a milky sap to flow into collection cups. This raw latex is filtered and stabilized at collection centers before being transported to condom factories. By the time it arrives at the plant, latex is a liquid suspension of rubber particles in water. Each batch is tested for purity, viscosity, elasticity, and protein content. Consistency is critical because even small variations can affect strength and thickness in the final product. Inside the factory, latex is first compounded. This means chemical additives are blended into the liquid latex to improve performance. These additives include curing agents, stabilizers, accelerators, and sometimes colorants or lubricity enhancers. Large stainless steel mixing tanks gently agitate the latex while maintaining precise temperature and pH levels. The formulation is carefully controlled. Too much accelerator can weaken the latex, while too little can prevent proper curing. Once mixed, the latex is filtered again to remove microscopic impurities that could cause defects. Next comes one of the most recognizable stages: dipping. Condoms are formed using ceramic or glass molds called formers, shaped exactly like the final product. Thousands of these formers are mounted on long conveyor chains that move continuously through the production line. Before dipping, the formers are thoroughly cleaned using chemical baths, hot water, and steam to remove any residue. Cleanliness here is critical. Any dust or oil can cause holes or weak spots. The cleaned formers are first dipped into a coagulant solution, usually made of calcium nitrate. This prepares the surface so latex will adhere evenly. Immediately after, the formers are dipped into the liquid latex. The speed of immersion, withdrawal rate, and dwell time determine the thickness of the condom. For thinner condoms, the dip is brief. For thicker designs, the former may be dipped multiple times. Gravity and controlled rotation help distribute the latex evenly along the former. After dipping, the latex-coated formers pass through drying and curing ovens. Heat causes the latex particles to bond together in a process called vulcanization, transforming the liquid coating into elastic rubber. Temperature and exposure time are tightly regulated to achieve the correct balance of strength and flexibility. If curing is incomplete, condoms may tear easily. If overcured, they become brittle. Sensors continuously monitor oven conditions to maintain consistency across tens of thousands of units moving through the line. Once cured, the condoms are no longer liquid, but they're still attached to the formers. The next step is bead rolling. Automated brushes or rollers gently roll the open end of each condom into the familiar rim. This rolled bead increases strength and makes the condom easier to unroll during use. The bead must be uniform. Uneven rolling can affect fit and reliability. After bead formation, the condoms are leached. Leaching involves washing the condoms in hot water multiple times to remove residual chemicals and excess proteins from the latex. This step improves comfort and reduces the risk of irritation or allergic reactions. Modern factories use long water baths with precise temperature control, sometimes followed by additional leaching after removal from the formers. Once leaching is complete, the condoms are stripped from the formers. Air jets or mechanical fingers gently remove each condom and transfer it to the next stage. At this point, the condoms are inside out compared to how they will be packaged. They are inverted later during finishing. The stripped condoms are dried again and sent to inspection and testing. Testing is one of the most critical parts of condom manufacturing. Every single condom must be tested for holes, not just sampled. The most common method is electronic testing. Condoms are placed over metal probes and rolled through an electric field. Because latex is non-conductive, any tiny hole allows current to pass through, triggering an automatic rejection. This test can detect holes far smaller than the human eye can see. Condoms that fail are immediately discarded. In addition to electronic testing, samples from every batch undergo air inflation tests. Condoms are filled with air until they expand many times their normal size, measuring burst pressure and volume. This ensures strength and elasticity far beyond real-world conditions. Water leak tests are also performed, where condoms are filled with water and checked for seepage. These tests are mandated by international standards and regulatory bodies. After passing testing, condoms move to lubrication and finishing. Most condoms receive a thin coating of medical-grade silicone lubricant to improve comfort and reduce friction. The amount of lubricant is precisely measured. Too much can make handling difficult, too little reduces effectiveness. Some condoms also receive spermicidal coatings or specialty formulations, depending on the product. Next comes drying and inversion. Condoms are dried to remove excess moisture, then inverted so they're oriented correctly for use. This process is fully automated, using air pressure and rotating drums to flip each condom without damage. Once inverted, the condoms are ready for packaging. Packaging takes place in clean room environments to prevent contamination. Individual condoms are fed into high-speed packaging machines that fold them into compact shapes and seal them inside foil wrappers. These wrappers are made from laminated materials that block light, air, and moisture, preserving the latex over its shelf life. Heat-sealing jaws close each packet, printing batch numbers and expiration dates at the same time. Each seal is inspected for integrity. Wrapped condoms then move to secondary packaging lines. Individual packets are counted and grouped into retail boxes using automated systems. Boxes are folded, filled, and glued at high speed. Instruction leaflets are inserted where required. Vision systems confirm correct counts and labeling. Finished boxes are packed into cartons, palletized, and prepared for distribution. Behind the scenes, quality control and documentation never stop. Condom factories operate under strict international standards such as ISO and WHO guidelines. Every batch is fully traceable, from raw latex source to final shipment. Laboratories inside the factory continuously test raw materials, in-process samples, and finished products for tensile strength, elasticity, aging resistance, and chemical safety. Retention samples are stored for years in case future analysis is needed. Environmental control is also critical. Latex is sensitive to heat, light, and ozone. Factories maintain controlled air quality and temperature to prevent degradation. Water used in leaching is filtered and recycled where possible. Waste latex is collected and processed to reduce environmental impact. Many modern plants are investing in sustainability programs to reduce water and energy consumption. What makes condom manufacturing remarkable is the combination of extreme thinness and extreme reliability. A condom may be only fractions of a millimeter thick, yet it must withstand stretching, friction, and pressure without failing. Achieving that level of consistency across millions of units requires precision chemistry, automated inspection, and relentless quality control. There is no margin for error. From liquid latex flowing through stainless steel tanks to high-speed dipping lines, curing ovens, electronic testers, and sterile packaging rooms, the entire process is engineered to produce a product people can trust without hesitation. Every condom represents dozens of controlled steps and multiple layers of testing, all completed in minutes on a continuous production line. And that is exactly how condoms are mixed, dipped, cured, rolled, washed, tested, lubricated, sealed, and packaged. a highly advanced industrial process hidden behind one of the most essential health protection products in the modern world. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, systems, and factories behind everyday products.